universe is calling me. It speaks both day and night. It's full of dark and light, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space, fields and forms, math and voids. It all sings with one voice. It's home. Boundaries set, foundations laid. Sound was heard, matter made. Solar systems from afar. Names and numbers for the stars, and I've heard others call from light years away, and they're real and they're here. Space and time are instantly clear. Planets spin, grids in place. We can travel through space. It's the Lord's.
Hey, welcome everybody to SkyTour live stream for this wonderful day. It's actually it's already going by like so fast. It's actually the 12th of February. Can you believe it? I'm Mark D'Antonio. Welcome if those who haven't been here before. And of course, joining me tonight, as always, is Daryl Mason. Hey, Daryl, how are you?
Hello, Mark. I'm good, thanks. How are you? Hello, everybody.
I'm doing fine, thank you. Things seem to be cranking along. I decided to stream tonight. You know, I had a dinner I had to go out to do, and that was nice and everything. And while I was there, I figured, you know what? I'm going to stream tonight. I want to start streaming, and I want to actually do something really fun for everybody tonight. So we're going to do a stream again, a typical stream like we always do. And it should be pretty exciting. So it's a beautiful winter sky out there in the desert, and we will take advantage of it tonight. What are we looking at here? Well, you know, not much right now. Let me just pull this down a little bit, shrink me down a little bit here, if I can, just like that. You don't need me full size there, so I'll be little down here, okay? There we go. Now, we're actually in Orion right now, and I'll show you where we are. Here, let me... okay, there we are. So we're right below the Orion Nebula. See that? This square represents our field of view. And it's a... The field of view is 1.5 degrees. You can see 1 degree, 29 minutes. Each degree has 60 minutes in it. So it's 30 minutes per half degree. So 1.5 of those. All right. By almost a degree in height. Sorry, guys, I had to sneeze. Wow. Anyway, so that said, we're down below here, and there's something down here I'd like you to see. Now, right now, this looks like an ordinary location, and what I'm going to do is I'm going to move us a little bit to the east, right? But first, I'm going to, get a different rate on my controls here. So as I control the telescope, all right, you'll see it's moving more gently. It's not sweeping across giant swaths of sky. And what I want to show you is this guy right here. Can you notice? Do you notice how that seems to be one of the only stars in this view that's fuzzy? And that fuzziness is because it's embedded in a nebula, and it's causing the nebula to light up with both reflected light and scattered light, which is kind of cool. The scattered light always looks blue. Reflected light kind of looks the color of the star, okay, because that's just reflected light. In this case, it's a star that's actually not a old star. It's kind of a middle-aged star, so it's actually got a color that's about whitish, so you'll see some reflection in there. So we'll center that up, and I'll show you this. Now, as we move up here, you're going to probably start to see, if not in this view, in the view to come, you'll see wisps of nebula up at the top coming down from the Orion Nebula. Now, that's pretty cool, and let's just move this down, and I'm going to move it over a little bit. So that's good right there. You can already see some nebula here. You'll see it when we start doing a time exposure. We're going to head to the east, take our telescope and point it basically to the left here in the view. Here we go. All right. All right, so now we've centered up this object, all right, and it's pretty near the center. Okay, and if we zoom in on it, we can see, make sure our stars are nice and sharply focused, and it looks like they are. So what we'll do now, I'll leave it right about here. And now I want to show you on our screen. We talk about this a lot, but I just want to show you just briefly, real quick, because we haven't done this in a while. One of the things that's interesting is that if we take a look, if we take a look at the nature of the way this system works, we see that this side right here, this is our telescope control cluster. This is our computer. We can look into the telescope, see what it's doing. Here are the telescopes right here. If I move myself out of the way, you can see the telescope in the building right there. Okay. And there's another view of the telescope right here. Then we have this here, over here. This is the camera cluster, right? That runs the cameras. We have the focus over here and everything. So that's pretty cool, and that's a neat thing that is very, very important for us to view and check out. Let's see here. So now, let me see if I can move this view around a little bit. Yeah, okay. All right. So what we'll do now is I'm going to set us up for an exposure here that's going to take us, say, maybe 25 seconds. And you'll notice I'm doing it for 25,000. You see that number over here. Okay. 25,000 milliseconds is 25 seconds. All right. There's 1,000 milliseconds in a second. And so what we'll do now is we'll now proceed to actually take this photo. And this is right here, this section right here is a quick processing histogram, it's called. Allows us to, show you what it would look like just normally and like that. And then if we enhance it like that, so now you can see that little nebula in there. All right. But we're going to do something beyond this. We're going to take this little nebula and we're going to actually stack it. We're going to take that image that was just taken and we're going to add it together with another image and just keep adding the data together. Because see how noisy this looks? You can see it has all this, like, this looks like it's got little tiny spots in it and dots, right? Well, we're going to add these, we're going to add all these together, and I'm going to change my setting here. We're on a filter. We're using a filter that allows us to capture things, make the stars round. So it's called a full width half maximum filter, which means that if the star images are round, then we'll use the image. If they're elongated, we won't. All right, so a red bar means they weren't round. Now we have a round one, so we'll see an image here in just a second. All right, there it is. There's the first image. And when you notice, okay, when you look at this image, you'll see it's actually quite dusty looking. But you also have these bright spots and these colorful modeling that's in here, which we don't want. So I'll get rid of that right now. We have this intermediate filter I can throw right in. Watch the difference. Ready? Click, and boom. So we remove a lot of the noise right off the bat, and then we'll just let this image build up. So what's happening now is we're taking an image, we're taking a second image, aligning it with the first, star to star, and then stacking it on top. And we just keep doing that, making an image sandwich. The more we stack, the clearer and the more detail we get to see if the detail can be captured in 25 seconds. So that's pretty cool. Marianne's here. Hello, Marianne.
Marianne is here.
That's right. And now what I'll do is say hello to the other folks. Shimmy Hinna, how you doing? I think I haven't seen you here before, Shimmy Hinna. It's nice to see you. Renee Cruz was first. And then we have Michael Hedrick. Hello, Mike. How you doing? And then looking down the list here, we've got Stuffy joining us. Stuffy, you've been coming back for a while now. I'm really happy to see that you're enjoying this. I talked to some folks tonight when I was out at the dinner, and they were very excited to see what we do here. Tim F. is with us. Hi, Tim. James Hyatt. Nice to see you, James. James is one of our patrons. That's really cool. Fantasy's with us. Daisy and Zoe are with us. Daisy and Zoe. Amethyst. Haven't heard about Lane lately. I hope Lane is going to come back and watch with you guys at one point. So that's pretty cool. And then let's see now. We've got... I'll go down the list here. You guys are pretty good. I said hello to Marianne already. Okay.
Hi, Marianne. So nice I had to say it twice.
I know, right? And we have Blindy Mitchie. How you doing? Nice to see you, brother. Nice to see you, and thank you for coming by. All right, so as you can see, we're making this beautiful image of this incredible little area within the Orion Nebula region. This is part of something called the Orion Molecular Cloud Complex, the OMCC, right? And let's show you some more detail here. So we'll drive this out. Now you can see there's clouds of dust and gas, and we're going to bring out even more detail by doing a color correction here, right? And this color correction shows you even more. And now to see it even better, let's zoom out a little bit to show you what you're really missing. Okay. All right, so there you go. So now you can see all this dust, and inside this dust cloud you have this feature here. This is called the 13th Pearl Nebula, and I'll show you where it is on our star charts. We come into the star chart here. This is our interactive planetarium that we use for doing our telescope movements. And so the 13th Pearl Nebula, this guy right here, right, is actually also known as NGC 1999 for those that are into astronomy. And for those that don't know, well, go ahead, Daryl.
No, sorry, the black spot was reminding me that I've seen this before. I see. Now it's the rubber stamp nebula, or also called the black eye nebula.
That's right. Yep, absolutely correct. And we, you know how we've seen this before. We've shown it to folks before. I could actually just kind of move this window over a little bit, and the people will see it right there, and we'll have a smaller view here. But this square represents our field of view, like I said. So it's 1.5 degrees by 1 degree in size. So to be honest here, let's go and back out and show you. There it is. That's 1.5 degrees across and 1 degree of sky high. Now remember, we have 360 degrees in a circle, all right? And we get about 15 degrees per hour that goes sifting through the sky as we sit there and stare at it. And it's interesting because if you multiply 15, all right, by 24 hours in a day, you get 360. So it's a 360 degrees in a circle divided by 15, all right, or divided by 24 is 15. So you actually see the relationship between degrees in a circle and the sky, and the passage of objects in the sky. Now look at this. I'm going to show you something interesting here. This is a very, very interesting location. And Daryl, you want to, right above all of this is Hiatsa, which is a star. Hyatisa, yeah, which we wanted to see before. Wouldn't
mind seeing it later tonight.
Yeah, it's right here, and it's just, we're going to probably go up and just do like a nice view. So we've got 13 exposures so far. Check out the difference from the first to now. If you notice, we're starting to see lots of detail in these clouds. And I haven't even played with any of the processing yet, guys. So we got a ways to go. So what I'll do is I'm going to take this down, all right? And I'm going to maximize this. Take out our view. We don't need that right now. So we can actually check this out in an uninterrupted way. But notice, okay, as we zoom in some more, we can do it now. Okay, you look here. This is the rubber stamp nebula, the 13th Pearl, NGC 1999. Same thing by any other name. And when you look at it, you'll notice that it's a beautiful, bright nebula, and it's got this dark object in here. That dark object, okay, is interesting because it's either a hole in the nebula or it's a dark nebula blocking something behind it. Well, I think in this case, we actually might be looking at a small void. I don't believe that that's actually a dark nebula right there. And this here, you'll notice this is kind of bluish. Okay, dust like this is all dust in here. This dust is actually very, very small grains of silicates and carbon, compounds and atoms and molecules. And what happens is the blue light from the stars is picked up by those pieces of dust and reflected back in all kinds of different directions. It's called scattering. The actual scientific process is called Rayleigh scattering, and it's the same reason why the sky is blue. All right, Rayleigh scattering, these particles scatter the high frequency light, which is blue, and that's why we see blue sky. That's why we see blue nebula. Okay, same process that's going on right here and right here. Very interesting. And this nebula right here, you'll see, is a mix of blue, and it's also got what looks like white in it. So there's some straight reflection going on in here, plus there is scattering going on. Right? Very interesting stuff. And Daryl, are you able to look up the nature of this dark object in here? I thought I remember reading in a paper that this was thought to be an actual void, which I I always thought this was a black, just a dark nebula obscuring what's behind it. But
you must have read my mind because I was just doing that.
okay.
Also known as the cosmic keyhole,
Yeah.
dust-filled bright nebula with a vast hole of empty space, represented by a black patch of sky. So I guess if they're calling it an actual hole, it's a void.
Wow. Well, there we go. Okay, so it is a void. That's right. It's pretty cool. I mean, I sort of remember that, but I couldn't remember directly. I couldn't remember directly. So that was something else.
Well, that's what propelled me to look it up because
Yeah.
I couldn't remember either. It sure rang a bell, though. I know we've been here before.
Yeah.
I guess this is why.
Yeah. Yeah. All right. So that's pretty cool. So that's interesting how that looks. And if you notice, this and this behind it are probably connected, because this is that dark nebula or dark dust that is in between us and what's going on here. You can almost see how this probably continues behind here through here where we can actually see it. You can almost see how that could be happening. And this dust, you'll notice, has a reddish tint. That's because it's not just dust here. It's actually hydrogen gas, neutral hydrogen atoms, that have then been ionized, so their electrons are popped right off of them with the energy, the ultraviolet energy of nearby stars. And then when they spontaneously recombine with the atom, they give off red light. Okay, that's the short form for what's going on here. But that's what makes what we call hydrogen alpha, or this reddish glow you see right here and right here. Okay, that's the hydrogen alpha light mixed in with the dark dust. Okay, and now if you look, you can see this dust much more clearly, and you can see actual depth and thickness to certain clouds. Isn't that beautiful? This is a beautiful region, and I'm going to actually name this NGC 1999, and that way when we save it, you'll be able to get this very image within seconds. It'll take about 30 seconds. I want to say hello to Cindy Murphy. I want to say hello to Kathy Prudisek, who's with us, and I want to say hi to Sam S. And I'm going to say hi to Rockstar. Why not? Because Rockstar just joined us, and he said hello. Cheers to you, too. Nice to see you all. Go ahead.
The article on 1999 here has something interesting to say about the keyhole, cosmic keyhole, or the whatever you want to call it, rubber stamp.
Mm-hmm.
It was previously believed that the black patch was a dense cloud of dust and gas which blocked light that would normally pass through, called a dark nebula.
Yep.
Analysis of this patch by the infrared Herschel telescope, which has the capability of penetrating such dense cloud material, resulted in continued black space. This led to the belief that either the cloud material was immensely dense or that an unexplained phenomenon had been detected. With support from ground-based observations done using the sub-millimeter bolometer cameras on the Atacama Pathfinder experiment radio telescope and the Mayall-Kit Peak and Magellan telescopes, it was determined that the patch looks black not because it is an extremely dense pocket of gas, but because it is truly empty. The exact cause of this phenomenon is still being investigated, although it has been hypothesized that narrow jets of gas from some of the young stars in the region punctured the sheet of gas and dust, as well as powerful radiation from a nearby mature star may have helped create the hole. So that's where we sit with it right now.
Very cool, yeah. And see, that's astronomy is changing our view of this, guy. So, that's one of the things that, again, I'm a professional astronomer. That's what I went to school for. And when I was going to school, getting my degree in astro, I can tell you this, NGC 1999 was known as a dark nebula with a reflection nebula associated with it. That's before we actually had all these studies that Daryl just referenced, okay? And it turns out that we change our understanding, and we get more understanding. And that's the thing about astronomy. If you don't understand something, give it some time, and the next thing you know, you'll either get reinforcement to that to help you understand it better, or you'll find a whole new hypothesis. And now with studies, we find out the true nature of that black hole right there. No, not a black hole like a star that sucks, okay, but a black hole like a void in space. Now that we have now 23, 24 stacked. Let's zoom in a little more, and this will sharpen up a little bit, and you can see that a little better now. So that shape right there is actually a little Y-shaped void in the nebula right here. Now we've talked about in the past, and for those that might remember, we've talked about this in the past, how you could have some stars that they're so hot and powerful, especially if they're born with other stars in a cluster, that they clear out a cavity around themselves within the nebula within which they were born. That's the kind of thing that we see in clusters. But when you have singular stars born inside of a dust cloud like this here, well, then their radiation isn't enough to push the dust away. Radiation does have pressure. You feel it on your face when you face into the sun. You feel the sun's energy striking your face. Now, there is a force to that. You can calculate the force of the radiation striking your face. It's tiny, but when you go outside, you feel it. All right? So that's the thing. You can feel that. We can measure that. And out in space, where there's very few other forces other than gravity, then small particles of dust that are microns in size can be pushed around, and gas, which is even smaller and even less massive, can be pushed around by this radiation pressure, we call it, and that will clear holes in space, move nebula. The shape of this nebula all over here, all this shape you see, it's caused by the radiation pressure from nearby stars. All of it. There's all this pressure, this buildup here, this arcing buildup here. Probably the radiation pressure created by a star somewhere in here, maybe something we don't even see, that's snow plowing and pushing this section along and causing it to bunch up, making it a little bit more bright and visible because it's higher density. So there's a lot of possibilities here, and all of these things happen out in the universe when we look.
If you look at the blue to the upper right of the star and the keyhole there,
this blue?
That's the scattered light. You say, the blue.
Yeah, you're right.
Really scattering. To look at that, you can see there's like a dark patch running diagonally up and down in front of it. It appears, and then the scattered blue light. Would that be coming from that star at the lower right, or would that be coming from a star behind the dark cloud that we can't see the source?
Any and all possibilities, because most likely it's coming from the star that's powering this down here, because this is probably up here, and so this dark dust is way up here in the foreground, and this darker area, this blue stuff, is like back here somewhere. So we're seeing it peeking out from behind this. So we're seeing it peek out from behind the dark dust in the foreground. That's what it appears to be right here. So most likely this star is probably also responsible for the scattering going on here, because it's doing scattering here, and quite a lot of it. So it certainly could be reaching this far as well. Now again, the universe is three-dimensional, so we don't know how far into the page or out of the page that really is. For all we know, this is a lot further away, and maybe this blue stuff is actually closer to us. We don't know. We have to, that's something we don't know. But I think it's all fascinating because sometimes we can actually see the three-dimensionality, you know. But that's beautiful. That's a gorgeous shot right there. That's going to turn into a beautiful processed image when we're done. Yeah.
There's a couple of links there in the chat I posted. The one towards the top of the chat box right now, that's a close-up of the keyhole.
Okay.
Really cool picture.
Okay. I want to say hi to Goblin, who's here. Nice to see you, Goblin. Goblin won our binoculars in our giveaway that we did with Calabos and Tiffany, who have entrusted us with doing all that. Let's see here. I gotta just mention, gotta tell them. Forgot to tell them. Okay. All right. So, if you notice here, is that again that orange right here? This orange is some of the hydrogen that's actually being caused to emit that red light I told you about, and there's a subtle red glow mixed into the brown of the dust here. It's sort of a mix of all these. It's a you know what it is? It's a stew. It's a cosmic stew of all of the many building blocks that are fundamental to life. That's what we're seeing here. All right, but this is really pretty. This is probably one of the best shots we've taken of this. If you remember in the past, when we've taken shots of this thing here would quickly get overexposed and be gone. But with the new camera, we're actually able to pull the detail out of this and still get all the subtlety of the clouds. So that's actually a win-win. Look at that beautiful cloud. Okay, I'm going to bring back in our imagery here. I'm going to dock it back to the lower line here. All right, and I'll bring back the telescope. There we are. Okay, now I'm going to save this just like we see it here. All right, and I'm going to save exactly as seen. There we go. So now there's a ping file that looks just like this out there. There is a astronomical fits file out there as well. So people that want to get into processing their own, they can see the raw file and process it in anything they want to, if they want to do it. But we give you everything. We give you everything. All right. So.
Give me a second. I'll try to get a link up to that.
All right. Thank you.
The server.
So now we'll come out of here. All right. And we're going to go back to looking at our enhanced night vision type view, night view, so that we can actually see where we are. So there is this beautiful subtle nebula. Now we're going to move upward, and as we move up, you'll see this really interesting nebula up here that you know so well. There's Hitasar. And there's the bottom of the Orion Nebula right there.
Tice is a really cool multiple star system.
Yeah, kind of like Sigma Orionis. But let's go up. We'll go up there and just do the nebula. These won't be contiguous. But I want to show this region to folks first. Okay. So now, that is our beautiful Orion Nebula. This is one of the few nebulas that you can actually see with your eye. There's Calabos. Got the message, huh, that I was streaming? Sorry, I forgot to tell you. If you look at Orion's belt, all right, let's go into our planetarium here. Back out a little bit. All right. Okay, if you look here, all right, this is Orion's belt, right? Alnilam, Alnitak, Alnilam, and Mintaka. And Orion, of course, is the famous hunter, and this is the mythology. You can see Orion the hunter, all right? And Orion the hunter has his belt of 3 stars, and then down below is his sword. Well, in that sword is this nebula that you can see with your eye when you look up into the sky, right? Now, you're also familiar with Betelgeuse, the big red supergiant star to the upper left in Orion, and that's on the opposite end. You have Rigel, the hot blue star at the lower right. Rigel is a very hot star. It's a star that's known as a type B star. B is in boy. Betelgeuse, on the other hand, is a red star, and it's like an M1A or something, M21A. I have to look and see here. I can't remember. But it's a supergiant. So so its spectral type is an M1 to M2 1A. So it's both, I guess. It's a hybrid. It's between the two. And what does all that mean? Well, the M letter tells you the temperature, and the Roman numeral tells you whether it's a supergiant or a star kind of like the sun, or a white dwarf or something like that, or a giant. Isabella's with us. Hi, Izabela. Good to see you.
Hi, Izabela.
And so the thing that's funny is that Betelgeuse is a far larger star than Rigel. In fact, you could put several Rigels inside Betelgeuse almost, okay? You could probably put at least 2 inside of Betelgeuse. It's so big. Maybe more, actually, because it's a sphere. So the bottom line is Betelgeuse is very cool on its outer environment. And the reason is because it's very, very far away from the stellar furnace in the core that's generating all the heat. But the pressure has pushed Betelgeuse's outer envelope way, way out. So if you put it where the sun is, it would actually reach all the way to Jupiter. I mean, almost to Jupiter. So that is a big spherical star. Amazing, you know.
Do you remember which one is actually bigger, Rigel or Betelgeuse? I mean, more massive. Rigel is a much younger star. That's why Betelgeuse is bigger. Rigel's an O supergiant, I think, and
yeah, Rigel
Betelgeuse is a red supergiant.
Well, actually, Rigel is a B8. Okay, the belt stars are O's, but Rigel's a B8. So it goes O1 through 9, O0 through 9, and then B0 through 9. So Rigel's almost to the end of the B's, B8. So that means temperature, and if temperature is a little bit lower, then I see your question, Michael. Hang on. And so when you look at a star like Betelgeuse, on the other hand, all right. Well, first of all, let's stick with this guy. Okay, Rigel is, yes, it's a massive star, and as far as its mass, we can certainly look up its mass for you and get the mass. Betelgeuse is brighter for one of the main reasons is its size, and because this other factor comes into play, and that's called luminosity. Stars that have evolved to near the end of their life sometimes grow to these massive red supergiants, and these massive red supergiants, because they're so big, they're very luminous. You can see them from far, far away. And so that's what we get with Betelgeuse. We can see it from far, far away. Betelgeuse, yeah, go ahead.
I'm sorry. Betelgeuse has about 16 and a half solar masses, and Rigel has 18 solar masses.
Yeah.
So Rigel actually does mass a little more than Betelgeuse.
Right, but that has nothing to do with brightness. That's the thing. Which
Well,
I know,
understand.
I know it's not what you were saying. But because Betelgeuse is so evolved, Betelgeuse has expanded to the supergiant stage, and even though it's less massive, it's actually brighter than a star that's more massive, and that's because it's bigger in size.
Exactly.
And that's what generated this particular, metric when we started measuring stars and putting them in diagrams. So we're down here in the Orion Nebula, so we're going to come back down here and focus on the Orion Nebula again. All right, so we're down here, and this star here is the Hittasa star that Darryl likes so much, and he likes Sigma Orionis as well. We may see that star, but I want to do something first. I want to take off. This right here, and I want to move this into the center because I want to show you what's powering this nebula. Okay, we come into the center here, and I can see we're going to do a focus adjustment, which is another reason why I did this. So we'll refocus these in a second. You'll see right here we've got 1, 2, 3, 4 stars in here. See that? There's actually more. All right, and we're going to focus it, and then once we focus, we will start the photography. The last photo was focused, and we didn't have that problem. But when a telescope moves, sometimes we get something called mirror flop. The mirror flops, and every telescope has that, even the professional systems. So it's not just us. All right. Well, we are a professional system, I guess. So right now, what I'm doing is I'm doing an automated focus procedure that's going to gauge the size of the stars, and it's not just those 2 that it's looking at. It's actually got 12 of them that it's looking at right now. You can see down here. Now it's 14. That number is going to get larger and larger as more come into focus. It could conceivably get up to 50 or 60 stars when it finally gets the focus done. And, depending on how much how many stellar objects you have in your field. Okay, in this case we got up to about 20 stars before it started to get out of focus. So what happens is, you see what it's doing? It's focusing and focusing, and then where it's the lowest here, this lowest point in this focus curve, that's the most focused position. And this is the discrete ones it took. It took this one, it took this one, it took this one, this one, this one. But what it didn't do was do that. See where it puts the line? It doesn't put the line on one of the actual measurements it took. It interprets mathematically where the lowest area is in the curve. And that becomes our best focus location. So we click best focus, and the telescope goes back across the spectrum of focus values and finds itself back here. So now when we come up, we now see that we have the trapezium, these 4 hot stars in the middle. They're primarily the 4 hot stars, but there's more in here than just those 4, right? And we might, I think I had a cloud in there go through because it had this little weird appendages coming off there. But let's drop the, I'm going to drop the exposure to 1/4 of a second because I want to show you what it looks like at a lower exposure so you can actually see the stars better. All right, let's see here. There we go. So now if I move this over, bring up the data a little bit. Okay, so you see 1, 2, 3, 4 stars. Those stars that are in there are actually hot young stars, and they're causing the colors and the glow that we see in this nebula. So we're getting an extremely hot set of stars in here, and again, not just these 4, but more. And they're causing these the atoms in this cloud to ionize, atoms of oxygen, atoms of hydrogen, other atoms, and when the electrons recombine with those atoms, they give off light. The green is oxygen, doubly ionized, okay, ionized twice, meaning 2 electrons leave the atom. And hydrogen only has 1 electron, And so only one electron will leave the atom. But when it comes back in, the predominant place it drops to is a certain level within the atom. We call it a quantum level, and that quantum energy state is at level 2 in the atom. There's several. And but they go to discrete states, and so that's why we have something called quantum mechanics. Quantum are discrete identified levels, and so these quanta dictate what we're going to see in the universe in terms of color. If oxygen is doubly ionized, we typically see green. If hydrogen is ionized, we typically see red. So because hydrogen is the most predominant element in the whole universe, it stands to reason we're going to see a lot of red in the universe. And because oxygen is the third most abundant element in the universe, it stands to reason we'll see a lot of greenish colors like in this nebula. So let's now do 25-second exposure here. And we'll stack it and bring that in as well. You can see the yellow progress bar over here. This tells you where we are in the process over here. I'm now going to come out of this and go into our live stack. And Daryl, if you had something to say, this is the time when you can say it.
Kevin Williams asks, how old are the stars, do we think? The whole Orion cloud complex there is full of young stars. I dare say you're talking more on the order of millions of years or less.
Yeah, a few million years.
Yeah.
And give you an idea, okay, Alnitak, the leftmost star in the belt, very, very prominent star to your eye. But, and I've told folks this before, when Australopithecus afarensis, known as Lucy, one of our ancestors, was walking around in Olduvai Gorge 4.2 million years ago, if Lucy managed to look up at the Orion Nebula, or the Orion location, Lucy would only have seen 2 stars in the belt, and the star Alnitak wasn't there yet. It hadn't been born. So within the last 4.2 million years, Alnitak was born. And it may only last another 6 to 8 million years before it goes supernova. It's a hot O-type star, and the death of Alnitak is going to be a absolute full-on blowout. It's going to be great, but I would like to see a supernova locally before I meet the stars.
You might remember Michael Hedrick had a question also.
Yes, he did, and I got to go back to it.
Yeah, he says, Mark, you think there has been enough time passed that the ancient Greeks would have seen the constellations any differently? You can jump in on that. There's something I'd like to add to that at some point.
No, take it. I'll add mine after. Wow.
The constellations would look much the same, Michael. Most stars don't move that fast. We've talked about Barnard's star before. It's the fastest proper motion star in the sky. It's so dim you can't see it naked eye, though. The constellations would mostly look pretty much the same. One thing that would be different, though, we probably talked about precession of the equinoxes in the past.
Mm-hmm.
That's where the Earth's polar axis is going in a great circle up in the sky. It's where they say it takes 26,000 years for the North Pole to point back where it was after it completes that big circle in the sky. That circle is 47 degrees across, which is, a radius 23.5 degrees, which is not a coincidence that that's the axial tilt of the Earth's axis. As the North Star moves around that big circle over the course of 26,000 degrees, 26 thousand years, what we would see is that the constellations would change places in the sky. That, like right now, Orion pretty much straddles the celestial equator.
Yeah,
well, a
let's
few
bring
thousand
that
years
up.
ago, it didn't. It was in a different place in the sky. If
and-
I had a hula hoop, I could show you what's happening, but
I'll show them here,
you'll just
Daryl.
I'm sorry.
I'll show them here on the screen. Okay, because what Daryl's talking about is, if I can, here's our North Pole. Okay, this is our North Pole, right, guys? Well, the Earth is like a top doing this. It's precessing. That's what he's talking about. But it's doing that, as he mentioned, every 26,000 years. So you can imagine it's going to draw out a circle on the pole here that will be a 26,000 year diameter. There are years in the past where the star Vega was very close to the North Pole, where the star Thuban in Draco the Dragon was close to the North Pole. Right now, it happens to be this star called Polaris. You know, Polaris is actually one of the closest stars to the actual North Pole that we've ever had. There really aren't any that ever go right directly on the very top of the Earth where it aligns with the sky. But this is what he's talking about right there. So the precession angle is somewhat like this, okay, about that big. Sorry, I just got rid of it on you.
Yeah. On a map, what would be the what we're seeing is the geographic North Pole, or the geocentric North Pole, whatever.
Yeah.
Polaris. What the center of this 26,000 year around circle would be is called the ecliptic North Pole, which is offset 23.5 degrees to the Earth's North Pole, what we see in the sky there.
Mm-hmm.
And as we progress around that circle in 26,000 years, you're going to see the constellations, the whole sky kind of not just revolves nightly like we see it night by night, but the whole perspective of the sky is going to shift
right
over the thousands of years.
This is the star right here that was closest to the North Pole. I think it was like 10,000 years ago, 8,000 years ago, Thuban. And this was the North Pole star. But wait, the North Pole's right there with Polaris. That's correct. But because the Earth is moving on its axis, these blue lines go with the Earth. They're part of the Earth's extension of its coordinates. So as the Earth is precessing, you can see how that central nexus of lines ended up being close to Thuban as it does this at one point. So it's right in here. So it's really kind of interesting watching this circle occur over the course of time. So as Darrow was saying, they'll look very different to us.
Yeah, it's something I tend to pride myself on my visualization skills.
Mm-hmm.
I can't even say it anymore.
Just did.
But trying to grasp that also, how the sky would change over the course of time due to precession of the equinoxes. It's almost too much for me to do well. Again, where Orion, you see Orion there on the stellarium chart right now, it's pretty much straddling the celestial equator, and a few thousand years ago it was not, and a few thousand years in the future it will not be. As far as what we see, as far as the zodiacal constellations go, the 12 signs of the Zodiac, in the sky, from the time they were established, we have shifted about 1 1/2 of those 12 signs in the course of the sky over the last few thousand years.
Yeah. And when he talks about the celestial equator, you can see here it says +0 right there. The equator runs right through the Orion's belt region, right near Alnilam, the rightmost star. So when you look in the constellation Orion, an interesting thing that you could do is you can draw a line through the belt to the left, and that'll take you to the eastern horizon. Draw a belt through to the right, and that'll take you roughly to the right hand, to the western horizon. So it's sort of a little way to guide yourself around the sky, too. Kind of cool. I'm streaming tonight because of the fact that we're going to get a very big snowstorm overnight. We're going to get like a foot of snow here, I guess. And that foot of snow, it could potentially cause a power outage. So I'd much rather have a night where I can actually show you guys something and not lose a day. You know what I mean?
Sounds like you're about to get the storm we had a few days ago.
I bet you that's true.
Pretty good snow here Friday through Saturday.
Well, bet that's true.
And Colorado being what it is, it's mostly all melted already. Down here at any rate.
Yep.
They really got hammered up in the high country. They were getting feet of snow up there.
Yep. Ronald mentions, you also have the Pleiades mentioned in the Old Testament.
One other point I'd like to make before we leave that, where the Zodiac has shifted about 1.5 signs in the sky as that whole big hula hoop in the sky has turned that far.
Mm-hmm.
Astrologically, I'm a Capricorn. I was born about Christmas, just before Christmas. But by the sky, I'm actually a Sagittarius and almost getting into Scorpius, because that's where the sun really is instead of where astrology says it is.
Okay.
And the same goes for you. Whatever you think you are, you're actually about 1.5 signs farther west.
Yeah.
And I'll shut up about that now.
No, that's all right. All right, so I was trying to show you something. Let me try something here and see if this works. There we go. So here's the precession that we're talking about. Because the Earth is on its axis, it's pointing here now, right? It's at a 23.5 degree. So 12,000 years from now, Earth's axis will kind of line up with Vega. So somewhere in the future, as I mentioned, Vega will be our North Star. And so that'll be kind of cool. It'll be much easier to see, and then they'll actually be able to say that the North Star is actually pretty bright, because really the North Star isn't very bright, comparatively to the rest of the constellations out there and the rest of the stars. But that's what the setup is. So because the Earth's wobbling on its axis, it keeps, the North Pole will point at different things. Okay, it'll be looking at Vega in the year 14,000. So you set your calendars, guys.
Neskovid has an interesting question.
All right, let me get back to our main thing here.
All
right, so let's get out of there, and jump back into here. Sure, go ahead, Neskovid.
He says, hello everyone. What's known about the progenitor star that created the Orion Nebula, and are there anywhere such similar stars? Nebula, I'm sure Mark will chime in on this, but my 2 cents, it's not so much the star that created the nebula as the nebula that created the star. Again, there's the whole huge Orion molecular cloud complex up there, and stars are coming to life and being blown up in supernova there constantly. The stars that we presently see, like the Trapezium there that Mark has up on the screen, the Orion Nebula, those have not been there nearly as long as the cloud complex has been. The Trapezium stars there in the brightest part of that white, those are what is presently lighting up that we call the Orion Nebula.
Mm-hmm.
But the cloud itself has been there a long time before those stars ever existed.
And the question about where that comes from goes back to what Daryl was sort of alluding to earlier, and that is all this gas and dust you see in here came from countless previous supernovae. Okay, Now, there was some original gas here from when the universe was created, hydrogen gas. Okay, the hydrogen gas is this red glowing gas you see here. Okay, now, yes, it could have been released from the envelope of a star sometime in the past, many stars. And this whole region is full of dark nebulae. And what I'm going to do is kind of show you. See the dark nebula here? You're seeing it silhouetted against some of the other nebulae here. But you're also seeing where it's green. This greenish color, this is not dark nebulae doing that scattering thing I was telling you about. This is dark nebula. I'm sorry, this is gas that's been ionized and it's glowing. Okay? It's very, very hot gas, you know? And so we're getting oxygen that's doubly ionized, making this green glow that we see here. And we're getting hydrogen that's singly ionized, 1 electron. All right, and it's glowing red as we expect it to. One thing I'm going to show you that's really interesting is that this is very tenuous gas. It's not dense. And I'm going to show you what I mean by that by coming down to this section right here. We're going to zoom in on this section right here, and I want to show you something really important here. We've got 30 shots exposed here, so it shows very nicely. Here is a hydrogen gas cloud. You see this little finger of red? You'll notice that you also see green, and you see the red through it. The red is pretty dense, but the green is not. You can actually see the glowing hydrogen coming through this green oxygen. That's a fascinating thing that to look at, because it shows you the three-dimensional layout of the nebula in some ways. But it also shows you the sheer chaos that created this region. Look at this region right here. This is actually an often looked at region. This region right here, this is a shock wave in here, a bow shock. All right, that's actually from a hot star in the region, and it's pushing the gas along. It ionized the oxygen, but it also pushed it along the way here. And this area here and behind it is being compressed. It's possible that someday another star system will form in here from this compression, because it's going to cause movement of gas and movement of dust, and the gas, hydrogen, enough of it, can start to spontaneously collapse into a dust cloud. All right, into a gas cloud that gets hotter in its center. And the more dense it becomes, the more stuff it'll attract, the more gas it'll attract. And it will just start to grow, spontaneously grow. When that happens, we can end up with star formation in here. And this is why places like this are called stellar nurseries. Orion is such a stellar nursery. But there's a lot going on in here. All these sweeping shapes are all formed by the radiation of stars and the way it pushes dust and gas around. This shape right here, pushed by hot star radiation, probably from the trapezium in the center here, sculpting the inside of this nebula. There might have been a lot more gas in the middle here, but because hydrogen is less mass than an oxygen atom, we see a lot of the green inside this nebula, but the red is more toward the outside a little bit. And that's because the hydrogen is easy to push away, much easier. It's a single proton with a single electron, and much of the time it's just a proton because the hydrogen is ionized. So that's much lighter than an oxygen atom, even a doubly ionized oxygen atom. So oxygen atoms tend to have the ability to stick around longer. So by studying how much material is still there and how much has been pushed away, that can kind of give us a clue as to how long the stars have been there doing the pushing, because we can model these stars and figure out how much radiation they put out. When I was getting my astronomy degree, I mentioned this before, that's exactly one of the things I did. I actually had to model a star to figure out how much radiation it was outputting. And the computer calculations are literally horrendous. You can only imagine how deep they have to go. But it was really impressive to see the results. You could actually look at the star at any point in its evolution and figure out what could be expected in the region around the star. So it's actually really neat. But that kind of gives you an insight as to how we think as astronomers and the kind of things we can do. And Michael Hedrick has another question. I'll get to that in a second, Mike. So here's this dust now. And this dust you see right there. It's sitting right over the front of this nebula, and you see it in silhouette. Notice the color. It's pretty brown. There's not a whole lot of red. What's that telling you? It's telling you that any hydrogen gas is not really present in this particular region, but there is enough dust that you can see the dust. There's more dust than hydrogen, so the dust color dominates the region right now, right? So whereas there is also dust down here in the red part of this nebula, the gas is much more dense than the dust, and so the dust shows up less, and we see more of the hydrogen gas. This is beautiful, Daryl. This is just so pretty. God, that's pretty. Look at that.
Per the question a little while ago, if you can see deep time exposures of the entire constellation of Orion, you can see a lot of the molecular cloud that the Orion Nebula is only a part of, illuminated part of.
That's right.
But when you see the whole constellation, you'll see a big red semicircle over on the east side of the constellation. That's called Barnard's Loop, and that's an old supernova remnant. That,
you might be able to see that.
Where generation after generations of stars being born in the cloud have been being born, lived, and died and exploded as supernovas.
Yeah, and that arc is right here that he's talking about. It goes right up here and around. Yeah.
Actually, there it is right there.
It should be on there, right?
It is on there. It's a little below where you're pointing. Right there.
Right here.
That's
there it is. Yeah, I got you. There it is.
But that's all.
Right there.
I mean, that's the big scale showing where there have been many stars in the Orion Nebula and probably many different looks at the Orion nebulas over time. And the deaths of one of those stars, or more than one of those stars, made Barnard's Loop the big supernova remnant we see now.
Yeah.
Just to the east. Mark, would you excuse me a moment, please?
Yeah, go right ahead. So,
Michael Hedrick had a question.
Yeah, I got you. I want to welcome Mindforked. Hi, Chris. How are you? Good to see you. C&D Boys with us. Michael Hedrick says, another question, please. Is there an event that could happen close enough to Earth to alter our night sky for more than hours or days, longer than a supernova or the past? The supernova of the past. Not really. For all the dynamicism of the universe, it's actually quite stable in terms of events. And short of things like an extinction level event, like a collision with an asteroid or something like that. No, I think that we're actually in pretty good shape right now, actually. This is gorgeous, though. Okay, we're going to save this, by the way. This is also known as M42, Mission 42. It's an emission nebula. That's what you see here. And this green is also the emission nebula. It also has reflection nebulae in it, and that's something that would be more blue, and that is something that we'll see next when we head up north a little bit here. Okay, so we're going to go up north. We're going to save this. Okay, and save it exactly as seen. Now to show you what's really here, let's do this. We're going to pull this in. This is the killer one. It shows you, look at all that dust. Look at that, huh? Look at all that dust in here. Absolutely crazy amounts of dust. All right. So what we can do is, let me drag this over. Okay. Isn't that wild? Look at that. All that dust. Okay, first of all, just so you know, it's just over 22 light years across here. If you were there, you might not notice that you're in the middle of a nebula. You might see the bright trapezium stars in there in your view, but you might not even see any red around. It wouldn't be like it's all red around you, okay? Because this isn't very dense. This is like 24 light years across here. Light years. And so, the atoms are so far apart from each other that it's only collectively from a great distance where you can actually see this color. You might not even otherwise know you're in it. Give you a perfect example. The Pleiades, all right, the Pleiades is a beautiful cluster of stars. And if we look at the Pleiades up close, like we can see blue dust around them. Well, until recently, we didn't know that it's possible that we ourselves are within that same dust that the Pleiades are currently traveling through. So that's a fascinating finding. And we didn't even know it. We didn't even know it. Isn't that crazy? C&D Boy says there's a supernova in Leo. Well, Leo's coming up right now. Daryl, can you get on that and find the supernova and see if we can possibly look at it? He'll come back. Okay, so we're going to save this one more time. And we'll save it exactly as seen. And we'll get out of it right now. And let's go back to our 1 second finder. All right, and there we go. There we go. And now we're going to go north a little bit because I want to show you this last stop in this tour of these objects. When Daryl comes back, he can look for the supernova in Leo.
Yes, thank you. I meant to do that.
Okay. All right, so JSCO 77, how are you? Have you used your telescope that you won from us? Put you on the spot. Oh, Renee Cruz, feeling lousy? I'm sorry. Well, hopefully we can get a smile on your face tonight. Okay, we're going to bring this down. JSCO says the weather has not cooperated. I know what you mean. This is the first stream we could do in a couple of weeks because we had alternating nights of cloudy, rainy, situation going on out there. Atmospheric river find its way to the coastline, and then into Arizona. Okay,
I'm sorry, I do not see a new supernova in Leo.
Okay.
Maybe I'm not asking the right question yet.
That sounds like the question to ask. All right, guys. Well, we're going to look at this guy right above the Orion Nebula. You'll see the Orion Nebula, and then this is the previous picture we took. All right, I'm going to clear it, and that's not what it looks like. I had this other processing adjustment way up high. Well, let's check it out. So this next object is the Running Man Nebula. This is right above the Orion Nebula. And we talked about the Orion Molecular Cloud Complex, the OMCC. We talked about the fact that this region is full of dust. Well, this is a reflection nebula, known as a reflection nebula, But really, when we say reflection nebula, we really mean scattering nebula. I'm going to try something right now. I'm gonna kill this for a second and bring it right back. It's gonna come back.
Okay, I have it.
Okay, good. Hold on one second with that. I'm gonna be right back, so you won't see anything for a minute, but then you'll see it back here in a second. Okay, there we go. All right, now this let me yeah, we're good. Okay, so move me over here. Okay, Daryl, tell me what you're looking at.
I'm looking at you.
Oh, yeah, no, I know, but in terms of the supernova.
Oh, well, C&D gave a clue. Hubble views the galactic supernova site January 19th, 2024. It's a small galaxy known as UGC 5189A, 150 million light years away in the constellation Leo. Galaxy was observed by the Hubble Space Telescope. This doesn't make sense. It was observed by Hubble to study a supernova explosion in 2010, known as supernova 2010JL.
Okay.
And I guess they saw another supernova looking at the old one. Okay, I think this is a new observation of an old supernova.
Yeah, because what they want to do now is go look for a debris field, the debris cloud expanding away from the supernova site. Yeah,
I think that's what they're saying.
Okay. Michael Hedrick, you're saying, what is that beautiful thing in the bottom middle? Are you talking about this guy right here?
SCA 43.
All right, that's Measure 43. Machane's Nebula or whatever. That was named by him. This is the top above the Orion Nebula. This is the rest of the Orion Nebula down here. So we just kind of went up above it. And now we're looking at this beautiful cocoon of stars with a lot of blue light. And this, again, see all this brownish, reddish dust? Here, the dust is mixed with hydrogen gas, so it's kind of taking on a little reddish brown hue. Here, it's only reflecting light from stars and not scattering it, so we don't see a lot of hydrogen in here, so this dust looks brown. It's silicate-based and carbon-based. And now this cloud here of dust, these stars are having their light scattered by the dust in the cloud. That's why it looks blue. We classically call those reflection nebulae, but in fact they're scattering nebulae. They are nebulae created by the scattering of starlight. All right, and that's what we're looking at here. However, deep inside this nebula, you see a kind of a magenta-looking nebula. Well, that's interesting because that magenta-looking nebula is precisely there for one reason and one reason alone. And that is because we're looking at a Orion-colored nebula seen through a blue reflection nebula. And the way light adds, okay, when you add light together, it's not like paint, okay? So when you look at it and you add it together this way, you'll see that when you add red light to blue light, you get magenta light. And that's what we're seeing. We're actually seeing an additive result of the red nebula coming through a relatively dense cloud of dust that is scattering a fairly large amount of light. So the amount of light that's scattered is pretty high, and so it's enough to change the color of this nebula within. This is actually an emission nebula inside of hydrogen alpha, or hydrogen, the singly ionized hydrogen, and it should be red. It should be the same color as the Orion Nebula. And it is, if you can get into this blue cloud and look at it specifically. So, but that's what it looks like. In between this, which is called the Running Man Nebula, because this looks like a running man. Here's a leg and a foot. This is a leg. Here's his arms. Hey, wait for me. An arm there and a head. Okay, that's why it's called the Running Man. And then you have this beautiful cloud structure here in between the two nebulae. Really stunning stuff. You know, I couldn't wait for winter to come so I could actually see this stuff. You know, JSEO says this imagery is as good as about anything one will see anywhere. I'm not going to say it's not, because I do think it's probably. I humbly say that I think that I did my homework to make sure this equipment could deliver. And thanks to Marianne Robb, who has been here in the chat, and to Tara Diulis, the other person involved with SkyTour Livestream, our nonprofit organization. With those two at the helm helping do this, it's been so much easier. They are amazing people. I could never do this without them. And then, of course, we have Daryl, who's here most nights we stream. All right. And we have Izabela, who does amazing stuff for us behind the scenes. She's an artist in her own right. So, on top of that, we have our new official volunteers, Calabos and Tiffany. And they've chosen us to be the exclusive distributing point for equipment when they do contests. And we give away telescopes, we give away binoculars, and we will be giving away night vision systems, the psionics auroras.
Izabela's going to be running this place someday.
Excuse me. You're probably right. Jesus, okay. Well, you know what? If Isabella's running it someplace, she will have earned it at some point. She will have earned it by then, I'm sure. You know, I have to tell you, we keep threatening, Daryl. We keep threatening, and Marianne wants to do this. We want to bring Izabela here from Bulgaria and show her the observatory, show her Arizona, show her what's up, where this is all coming from and where it's happening. She's done an awful lot for us, and we'd like to do that. And she's like, no. And we're saying, yes. So when the time is right, we're going to do that. And now she's sitting there. She's probably shaking her head. Oh, no. But that's one of the things that we'd like to do.
Cool.
This is really sharpening up, huh?
That's nice.
Yeah, we'll zoom in, show a little bit. Actually, let's get rid of this, okay? And let's get rid of my. There we go. And now we'll zoom in. Look at that! Wow, really pretty. Very nice.
I wonder how many Orion nebulas there have been through time. You like to talk about Lucy. She probably saw a different Orion nebula than we do.
If this nebula was there, then the Trapezium stars are probably younger than 4.2 million years, so this nebula probably didn't exist back when Alnitak winked on.
Yeah.
And then it came in sometime after, based on the age of the Trapezium stars that we can figure, most likely. You know, but it's incredible. And here's something to think about, guys. If you see this dark dust, there's many stars in here we don't see because they're within the dark dust. And now there's hot ultraviolet radiation coming out from down there in that nebula and heading up into that dark dust. It's getting there, okay, because it's certainly ionizing oxygen that's out here. So you can imagine it would ionize stuff out here if it could get there. However, the big thing that's interesting about dark dust is the dust is a shield against ultraviolet radiation in a lot of ways if it's dense enough. So maybe inside this cloud right here maybe, there may be, we don't know, there might be a star with some planets around it. And there's no reason to suspect that this area is going to be bathed with killer ultraviolet radiation that wouldn't allow life to develop, because this region is protected. It's a protected, shielded little alcove that would be protected from destruction by ultraviolet radiation. So I think that when you see a dark nebula like this, this is why I've said many times before, life began in the dark. And so in the dark in the universe, that's where the sun was developed, in a dark cloud like this with gas and dust. And there was enough dark nebula around our early solar system to prevent it from being completely sterilized by ultraviolet radiation from other nearby stars. Now, we've gone around the galaxy just about 20 times. This was it, 220 something million years per revolution around the galaxy. It takes us to orbit the galaxy. And in that time, we've gone by other stars. We've gone through dust clouds. We have entered and left nebulae over that time. So who knows what it was when we were first born. In fact, when we were first created, when the sun was first created, our star was born with other stars exactly like it. Okay, so when you look at a cluster of stars, all the stars in the cluster are nearly identical in chemical composition. And so to find other stars that are like our sun, if we find another star that has the exact same spectrum as our sun, then that's a pretty good guarantee that it's what's called a stellar sibling, a star that was born within the same nebula as we were. Now, for a period of time, the Big Dipper itself was thought to be a cluster of stars that we had been part of, because they're actually moving through space themselves as on a trajectory that just happens to be a trajectory that they're going through space on. And in that trajectory that they're moving through, we see that, in fact, the stars are moving in a different direction than we are. So the fact is, we aren't part of the Big Dipper. So that started a search off in the direction to try and find our actual stellar siblings. And we found something that was interesting, and that was there's another star that is literally identical to the sun. That star, it's in the southern hemisphere. We can't see it from here. Because, again, as I said, we've gone around the galaxy a number of times. So the stars drifted away from each other. So where we were born is now a totally different place from where we were. And who knows, we might have gone through it several times in our orbit. Don't know where that would be. But we did find one sibling. Izabela says, hey, they discovered something incredible. The Bennu asteroid comes from a planet that was an ocean world. I am not sure where that's coming from.
That was out some days ago.
What was the actual story?
I'm sorry?
What was the actual story?
I forget the details. They finally got access to the samples from the Bennu asteroid.
Yeah.
They got the lid off that spacecraft.
Yeah.
And something they found inside looks like it came from a water world.
Suggesting that it came from Earth at some point?
No, they saying it came from a watery planet, an ocean world. as Izabela said. I don't know if that's over dramatizing it. It may have come from a wet environment, perhaps a Sears-like body. Ceres.
Yeah, Ceres is a well-known wet, quote-unquote, dwarf planet. And what Izabella is saying is they detected some compounds in the asteroid that can only be formed in the presence of lots of water. So that's pretty cool. I'll have to look that up and report on it to you guys in just
I'm
next
looking
stream
now.
or so. Look at this. This is like a painting, what I'm looking at right now. This is like a painting, guys. Painting, man. Wow. Isabel says it was an eerie resemblance found in vapor shooting from beneath the icy crust of Saturn's moon Enceladus. Interesting, because Bennu was thought to be a rubble pile asteroid. And a rubble pile, you're welcome, JSCO. A rubble pile asteroid is one where mutual gravitation just pulled a bunch of debris together and formed an asteroid. Now, is it possible that over billions of years material got stuck in there and possibly now and then it escapes and jets through the surface? Yeah, it's possible.
Here's an article from space.com. The headline is First look at asteroid Bennu samples suggests space rock may even be a fragment of an ancient ocean world. So put that in your pipe and smoke it.
I wasn't doubting it.
Yeah,
I wasn't doubting it.
It's a pretty dramatic headline.
Yeah.
Plus it's space.com, so.
Yeah.
Still
Look at this.
scanning.
Oh man, we've got this is beautiful. Okay, we're gonna come out of this now. This one's beautiful. We're gonna save this. This is Running Man.
Bennu samples contain plentiful amounts of water locked up in minerals like clays and are also rich in carbon, nitrogen, sulfur, and phosphorus. OSIRIS-REx samples represent the largest pristine reservoir of such material on Earth.
Yep.
We're going to be busy for a long, long time.
That's right. Wow. I gotta say, OSIRIS-REx, amazing space probe. When the OSIRIS-REx team put out a call for, they wanted to put a microdot on the OSIRIS-REx spacecraft that would contain imagery and work of scientists that made it all possible. I immediately thought of an astrophysicist woman that I knew, a good friend. She passed away. She was actually a Catholic nun, which I've told you about. Her name was Mary Ellen Murphy. Any relation, Cindy? Cindy Murphy? Mary Ellen Murphy was a Catholic nun who worked in the Hartford Diocese, I think. I'm not religious. I don't know. Sorry. But she was this unassuming little nun that was sitting at my dining room table with another sister who was a relative of the family. And she said she liked the Hubble Space Telescope. So I said, I got some color pictures I'll print out for you. Oh, please do. I thought she was just this little white-haired old lady. I didn't know. So then I go down, I come up, and I'm sitting down with her with all the pictures and explaining to her things like what we're talking about here. Well, this dust here, this is sort of like the foundational building blocks of life buried in here. And life started in the dark, and I was telling her things like that. And the other nun was starting to laugh at me. I go, what are you laughing at? Her name was Florence. What are you laughing at me, Florence, for? And she just gets, after about 15 minutes of this, with Mary Ellen just sitting there nodding and loving it, She goes, I can't stand it anymore. The Florence, the other one. She goes, what? I said, she's an astrophysicist. I was like, what? Well, the reason that she was so important in astronomy is because she was one of very few humans that have actually landed on an asteroid with a probe. And that was the Near Earth Asteroid Rendezvous project. She was on that project, and she was there and part of the team that landed on Eros. And I was like, oh my gosh, really? I'm not worthy. And she laughs, you know. But see, that's an example of someone who doesn't let any of her fame get in the way of actually really enjoying and loving the science. And I thought that was pretty impressive. So that was pretty cool. So she's immortalized now on OSIRIS-REx because I gave her name to the team, and they're like, oh yeah, this is perfect. So now she's on the OSIRIS-REx probe, where she will now be orbiting for billions of years in a big solar orbit long term, and that's gonna be pretty cool.
Cool.
Yeah, it's really cool. All right, I'm gonna save this now. This is gorgeous. All right.
One thing that article said that Izabela alluded to, and I think Calibos may have also, the phosphates. What they found on Bennu were like phosphate coverings that are typical of water worlds, not necessarily outside this solar system, but, and as Calibos mentioned, Enceladus and other thought to be watery moons or worlds in our solar system.
Yeah,
they had this phosphate present, and they found that present on Bennu.
Yeah, I wonder if an early Mars might have, had a lot of its atmosphere blown off by something, and Bennu was the result of part of that, perhaps.
Perhaps.
Not unlikely, but it's no less of a theory than anybody else's.
Sure.
All right, let's go to 25% here on our view, and there we go. Now we're going to come here, and let's back out a bit. I want to take us back up this way, right here. Actually, down here more. Right there. I'm going to take you to a region now that's less hot than the region we've just been looking at. A lot more dust, some soft emission. Right there, you'll see this is reflection nebulae here. I'm going to move us up a little bit so I can show you a little better. But this is an example of a location where life like ours could have evolved, okay? And the reason is because this isn't one of those exceedingly hot regions, but it's also a region that's protected because of the dark dust. Who knows what the universe really looks like? Because we might be in this dark dust, so a lot of it's getting potentially blocked. A lot of the universe is potentially being blocked from us, right? So this is good right here. So we're starting to do our over there. You've seen our system. We actually have numbers now, and those numbers are indicating we're guiding, and we're guiding successfully. So this will be a 25-second exposure again. Let's do that. All right, 25,000 milliseconds, and it'll automatically revert to seconds. And we'll start our live stack, and you'll see the previous image in there all overexposed because this is in there. So if I get rid of that, we will clear that out. All right. Now our full width half maximum is set around 8.74. I'll leave it on there for now just to see where we get. The smaller that number, the better the stars. Okay, so it's going to work. It's down to 6, so I can drop it down and make sure that all the exposures are going to be at least 7.45 or less, because that way we'll get perfect stars. So this is a region of lots and lots of dark nebula. Hey, old schoolie, how are you? Okay.
If you do Casper, you have to do the boogeyman too.
Well, I'm going to think about it. It's a good point because it's on the other side of Barnard's Loop here.
Yeah.
Okay,
Barnard's
so
Loop is just to the left in this image, and
yeah, it may not be visible. It might be visible just peeking in a little bit here.
yeah. If we look at the boogeyman, it's right on the other side of Barnard's Loop, just next door.
Yeah. Old school, hey man, it's good to see you. I'm glad you slid on by. Love to have your company out here. Richard McFarland says, Witch Head. Actually, Richard, a good point. Next to Rigel, we've had the Witch's Head Nebula, and we've shot it before. Probably not going to do it tonight, and only because it takes an awful lot of exposures for us to get it to show up well. But we'll be happy to do that again. I hope you please stop by. Also, SkyTour live stream is one of the few live streams that actually gives away equipment on a lot of our nights. You can win whole telescopes. You could win binoculars. You could win night vision systems from Aurora, the Psionics Aurora Sports. So we're looking at that. We've already given away several items. If you go up to here, this link up there, skytourlive.org. Skytourlive.org is where it all begins. And to the upper left, you can come here and see SkyTour live stream. To the upper right, you can see our Patreon. Become one of our patrons. And if you scroll down on skytourlive.org, you'll see a blue box. It'll show previous winners of equipment with their handles. Okay, so we've got a number of these things that we've given away already. And if you look in the chat right now, ERT Radio, Ronald says, I won binoculars. Thank you. You're welcome, Ronald. Ronald's also a member of our Patreons. He's fantastic. And Izabela says, here's the Witch Head Nebula that I did yesterday. I hadn't streamed, but I found a spot in the sky when it was going to be just a little bit clear. And so after I got back from the Super Bowl, I actually shot that, and I think that I don't remember what time it was. But it was pretty late when I actually started going after it, and the sky wasn't too good, so it was all right. So here are the two stars that are in this nebula. There's this beautiful dark nebula that's up in the front here, and there's a blue scattering nebula behind it, this reflection nebula, and you can see this dark material starting to form here, and you can see that it's showing up better. There's a lot more up here, a lot of detail in here that will be coming out shortly. We've got 9 images stacked here, and let's see what our images show us here. That's a little better, yeah. Now the way this works, okay, these are our curves, okay. You see red, green, and blue curves. When you do the color correction, all right, it brings all the curves under each other, so it makes sure that you're not slanted toward the red, the green, or the blue. And that white curve is the average curve and for all the data. And this is our black level. If we move it to the right, over the top of the curve and then down, we're going to start to lose data, as you can see. Okay? Now that's good if you want to start looking at some details within the nebula, okay? But generally, we stay away from that. We typically go to just the left side of the peak. If you go too far off to this side, then it adds too much data that's not there. It's literally adding noise to our image. This is a very dark site, and so we don't have any problems with light pollution where we're looking right now in the sky at all. In fact, we have very little. Our next site, we've got SkyTour Livestream West is this one right here that you see. We have a second Western telescope going in very soon. I keep saying that, okay? But I'm going out there later this month to look at another site that's been identified for us. And we'll see if it works. And then if so, we're going to put another one in there, another telescope there. And then out here on the East Coast, we had a telescope that was in our observatory here, which you can see it back there. All right, but let me actually let me turn on the highlight for you so you can see that. So if I actually highlight that back there, now you see that telescope back there. Okay, that was the East Coast telescope. All right, and what we're doing is I'm actually thinking we may replace that telescope entirely, and out here put a smaller installation just for doing solar astronomy, so people can see the prominences and all the major eruptions on the sun. Now that'll be a daytime stream. Obviously, you can't do it at night, but I think that's probably where we may go. We may be selling that telescope back there, so we may do that. And then with the money we get from that, we'll use that to put toward our solar system telescope. The other thing too to keep in mind is that if anyone wanted to buy our equipment, that money is all a donation basically in exchange for the equipment, so you'll be able to write all that cost off on your taxes if you were of a mind to do that. And that's a 10-inch telescope back there, Schmidt-Cassegrain system, f6.25. Okay. As you can see now, you can see there's some subtle detail coming in here. This is really pretty. Let's really overdrive it here just to see what's in there. So now you can see there's all kinds of dust in here, and you can see this real complicated, it looks like hair. Okay, very, very complex region. To get rid of the noise. Alright, we've got 20 images stacked here. And let's just pull this up and then bring our dark level right up to just about the peak and make it about as dark as we can get it without losing any data.
Can we zoom in on the brightest part a little bit?
Yeah, I was going to do that because there's some nice detail showing up.
Yeah.
You're going to see both in these. There's lots of nice detail here, but let's zoom in on both of these and I'll do that.
I was curious about the edge of the cloud there in the lower part, just immediately above the bright part.
Okay, yeah.
You can see those wisps and tufts.
Yeah, there's some right here. You can see these beautiful wisps in here. That's really nice. Those wisps he's talking about are like right here. Okay, and there's one really interesting one right there. Okay, another interesting one right here. So there's really interesting, some really interesting detail in here. Now what I'll do is, because we zoomed in, I'm going to take down this level here a little bit. Yeah, you can see there's a lot of detail. And we've got 23 frames in here. The more we do, the better this is going to get. And let's go up to this guy now. This one actually has more detail in it. If you notice, it's got a lot of really interesting details in here that I think are really fascinating. Yeah, there we go. So this whole region is full of tremendous detail. Now, again, you'll notice there's not a whole lot of that red hydrogen alpha. There's not a lot of oxygen that's been ionized here. And there's oxygen here, just not a lot of it. Now, when I back out, you can see now how much dust there is in here. Look at all this dust. This is really an exceedingly dense area of dust. What that means is that if you were in the middle of it, you'd probably see many of these stars because the dust is really spread apart. Okay, so as an example, Daryl, if you could look up the distance. Wait a minute, you don't have to. I've got it here. Let me just come in here and pull ourselves in to this guy. Casper friendly goes. Distance is well, yeah, okay. It was about, I was going to say 1,500 light years. It's about 1,600 light years by this. It may be wrong, but at 1,600 light years, these stars right here, if we look at these two stars in this photograph, I can measure their distance apart, knowing they're 1,600 light years apart, and again, it's in 3 dimensions, but they'll be closest if they were the same distance from us. So I could get their closest possible distance from each other and give that to you once I calculate it. But I'd guess that they're only a few light years apart from each other. But the distance from here to here is probably going to be more distance than the distance from here to Alpha Centauri. And between here and Alpha Centauri is 4 light years. It'll take us about 10 to 12,000 years to get there at the fastest possible speed we can go. So clearly, this isn't something that we have to, or nor is it something that we would actually ever, traverse. I'm just saying that it gives you some scale to the universe here. And then the distance from this one to this one is several light years at 1,600 light years away. So that's why it'll all look very different if you're inside of it, because this dust and these reflection nebulae, the brightest parts might show up as a blue, a very, very faint blue haze to you, or they might not show up at all if you're in the middle of this. It might be pretty black to you. Your sky might be pretty dark because the atoms are so far apart from each other that you only see the conglomerate from 1,500 light years away, But if you're in there, this is everything in your universe is all around you with all this light, and you wouldn't see it. It wouldn't be a big bright blue sky. This isn't time exposure, right? It would just look like stars. You wouldn't even see anything like that. You can start to see there's a little subtle cloud developing in here that we're picking up with all this detail. This new camera that we're using is just phenomenal. There's another star that's illuminating this section of this cloud, but down here, if we zoom in on it, you'll notice that part of the cloud, the star is hidden by this dark dust. See that? That's pretty cool. Okay. So let's back out just enough to start to see this dust here. Look at that. Wow. Now let's kick this up a bit. and let that settle in. There it is. What a complex, messy place this is, huh? Hey, Wayne Pinkham. I gotta say, Wayne Pinkham, he went to Mauna Kea and went up to the observatories. And you know, he brought me a t-shirt back. This guy is phenomenal, really cool guy. He brought me a t-shirt back that showed the sizes of all the mirrors on top of the mountain. That's the Hawaii Observatory up there. It's at 13,100 feet or so. And he visited. It was really cool. And it was very nice of him. And he brought me an Oumuamua postcard, which I have, and really cool. So every time he comes on, I thank him for that because it's really cool.
My boss years ago, he married a Hawaiian girl, and he started spending time over there. He knew my interest in astronomy and stuff. He brought me back a blue Nalgene water bottle with the Mauna Kea logo on it.
Oh, that's cool.
Very proud of it. I can see it from where I'm sitting now.
Wow, that's very nice. Yeah, in the summertime when I just wear t-shirts, I'll wear the shirt that Wayne got me. Because I don't want to cover it with a sweatshirt or something, you know?
Yeah.
Ronald says 13,000 feet would make me dizzy. Yeah, it probably would, Ronald, considering that newcomers to the mountain that have to work up there sometimes will need a little oxygen punch to help them along, and they have to move slowly so as not to get dizzy because there's less oxygen up there. I remember flying in the open door of a Army aircraft when I was actually photographing the skydivers jumping out, and we're at 12,500 feet for about 3 hours. And when if you put your hand out the door, you heard this screaming high sound of the wind hitting your fingers, and it was 225 mile an hour wind, you know, so it's like whoosh, oh wow. And when the skydivers got in the door to jump out, they would stick their heads out, and the skin would be plastered to their skull. And I got photographs of them looking like human skeletons. It's really cool. Yeah. Wayne says, I was posting drone videos. I saw where you and saw you were live. Yeah, that's very cool. Thanks for joining us, Wayne. I'm glad you came in. Yeah, okay, we're up to 36 images now. We've only rejected 4. Let's find out where in that process we rejected them. Okay, 2 consecutive ones, 1 there, back out a little, and 1 of the early ones. Okay. Nice. Very nice. Now this is a beautiful image. I will change its name. And we'll call it Casper, the front. It's actually measure 78. I'll call it M78. M78, and I'll say Casper. Very good. Okay, we got 37 images. We'll save that here. And save exactly as seen. Now, the links that you've been seeing take you to skytourlive.org up here, okay? And skytourlive.org will allow you to see all of the images we took tonight. That's right up here, okay? Go up to skytourlive.org, all right? And when you get there, scroll down and you'll see a heading that says take me to the cool pictures. I want cool pictures. And read the instructions there, and it will take you to the directories where all of our imagery is landing. So that observatory that you see right there above me, that's 2,500 miles from me out in the Arizona desert. I'm in Connecticut running it from all the way on the other side of the United States. And when the pictures are taken, It ships them up to the cloud and then ships them down to our OneDrive server that we set up for you. I'm not sure what the server is, but if you go to skytourlive.org and scroll down, when you go to those directories, you're seeing the photos that were literally taken just 30 seconds ago in the building. Hey, Daryl, thank you for putting up the links, by the way.
Yeah.
I think Izabela fell asleep again.
Poor Izabela.
I don't see her anymore. I think she fell asleep. That happened to her one other stream. She said, "Oh, I couldn't stay awake." She's in Bulgaria. So for her, it's the middle of the night. So I cannot blame her. You know.
Middle of the night. It's 7 o'clock in the morning over there.
Is it now? So
7:16 a.m.
Okay. Gotcha.
There she is.
Okay.
We appreciate your dedication, Izabela.
Oh, absolutely. That's okay, Izabela. You're always so very helpful to us. No one ever asked you to do it, and the fact that you do shows how much you love what we do. So, like I said, and Marianne's with me on this, we're going to fly you over here from Bulgaria to hang out in Arizona. And you'll see what it's like out there, and you may not want to go back. This is beautiful. Okay, we're going to save it one more time with 41 images saved here. Stacked. All right. I think I just did it. There we go. And then we'll save it exactly as seen. There we are. There we are. And there it is. So what you actually get when you go up there, this is the image you're going to get. All right. Okay, there's the image right there. That's the image you get right there. Okay. And you're free to do what you like with it. All right. So that said, I'm going to come out of here and go back to our 1 second here. Izabela says, I've learned so much here, and it's cool when I talk to people and I know what I'm talking about. Well, you know, it all comes down to whether it's told to you in a way that you can understand it, right? And if we threw equations at people, and you know, if I wanted to talk about like Rayleigh scattering, and I went through an equation of how Rayleigh scattering works, oh sure, we could do that. But what's the point? Why would that be helpful to anybody, you know? So, you know, it's just what it is. All right. By the way, I just got a call today from Roswell. They asked me to speak at their conference. Actually, the city of Roswell called the people that do the Roswell Festival, the Roswell Daily Record, and said, can you get that SkyTour live stream to do a live show for us in July? So they're actually going to bring me out there to do a live SkyTour on site. They specifically asked for it, so I thought that was pretty cool. Now the pressure's on to do it. Okay, Boogeyman.
Is this the one that you had how to put it? There were an obstacle or two when you did it last year, but you did it.
Oh yeah. Last year when I did it, what happened was
you did it on a bed sheet or something, didn't you?
Oh no, that wasn't that. That was I think you're talking about Contact in the desert, which I'm also going to be doing this in. This was actually the problem I had. First of all, I got to find this. It's LDN 1655, I think.
22.
That's right, 1622. All right, there we go. And okay. Yes, no, I had to actually try to do the whole thing on a blow up screen that was blowing around and getting knocked over a couple times, and that was no fun. Okay.
Yeah, it's LDN 1622. The boogeyman. That's just to the left or upper left of Casper here.
Yeah, it is, and I'm trying to get my trying to get it to type in. I was having problems with my typing. That's what I want, and that'll come back up above the horizon. All right, that's better. Okay, so we'll zoom into this, and it's called the Boogeyman Nebula. This is actually pretty cool. Again, another region where there's some dark nebula, but a lot of it is a hot region that we would not want to go to. I wouldn't survive there.
If you look there on your Stellarium page, Casper, the friendly nebulas down there at the bottom right, and then that red band is part of Barnard's Loop, and then the Boogeyman is just on the other side of Barnard's Loop from Casper.
That's right. That's right. Okay, and I think, if I recall, let me go into here. There's that red star. So we're actually, that red star is right here.
Yeah.
All right. And so what I want to do is I want to bring that red star up a little bit. There we go. All right. There we go. So we bring it right about there. And now we go here. And that is about where we want to be. Because it's just to the left of it. So right in here is where it is. So I think that a little bit to the east. All right, take that red star just to the edge of the field, and we should be good. Because this is the bottom of it right here. All right. Okay. All right, so you see searching. We're searching for a star to guide on. Meanwhile, I can set this to a 25-second shot.
Izabela, probably, or maybe a majority of them. What we
What's
know
the question? Read the question.
All right. Are the planets of all red stars tidally locked? M stars, red stars. Red dwarfs, I assume she means. Quite likely, because they tend to be very close to the stars. Or at least what we would think of as the Goldilocks zone is going to be very close. And if they're very close to the star, they're probably tidally locked.
Yep. Well, in fact, when we talk about those small red stars, Izabela and everybody else, it makes more sense to talk about Jupiter than it does to talk about the sun and its planets. Jupiter and its moons are more celestial dynamically appropriate to talk about. I'm going to move this because of the fact that Jupiter is actually more the size of the red stars than the sun. The sun's almost 1,000,000 miles across, and the red stars are sometimes a tenth of the size of the sun. So it approximates more of what Jupiter is. So it's pretty interesting how that works out.
Bonnie's here. Hi, Bonnie.
Anahata 77. That's got to be Bonnie. Hi, Bonnie. Okay. Right. Let me look at the stack one more time.
I know there's an upper part to it if you'd even want to drop it down a little bit.
I'm gonna, yeah. I was just looking at the stack to see.
Or move the telescope up, I guess.
Yeah. I don't want to cut off the bottom, that's all. I think this one more jog. This might do it. Okay. Now we'll go back and do this again. 25,000 milliseconds or 25 seconds. And we're guiding safely. That's good. And we will now bring up our stack again. Turn off this because it just blows everything out of the water. Yep. And so now we've put this down here, and let's clear this and see if that comes in. That'll work.
Yeah, that shows you the main part of the boogeyman lower down, and then you got that extension there at the upper left.
Yep.
See the
That's
dark
good.
clouds up there.
So this is what they call a boogeyman. And many of these objects are named for the fact that there is a shape or resemblance to something from mythology or popular culture, depending on the age and when this was identified. So it's a nice night. If you look where the telescope's pointing, it's pointing almost up high enough so that we shouldn't have any any problems with the air we're looking through. Because the air we're looking through makes a big difference.
Yeah.
If you're looking close to the horizon, you might see less detail because you're going to be looking through more air. So that's how that works. Now, we've got 3 captured. We rejected 1. Let's go find out what our settings have to be for this one. Ah, we're good here. 7.45 is going to be good. Very nice.
It is 10:30. All the bright stars of winter are now west of the meridian. I'm here at my place. You're about a half hour behind me, sky time.
Yeah, they're still west.
Yeah. Actually, Orion. The other night, Orion's getting ready to set. Orion is setting by 1:30 in the morning now.
Yeah.
Time flies.
Yep. Right now here it's been actually clear for days straight, and then it has become cloudy tonight because we got that big storm coming in, you know.
In Arizona or Connecticut?
Connecticut.
Yeah. So we were saying earlier, that's probably the storm that hit here a few days ago.
Yeah. I mean, I'm in the control, room here for the observatory. So we're safe in here, obviously.
Sure.
I prepped outside for the potential for the storm, I should probably do a tour of the facility here so people can see where this all comes from. I mean, we have, you see the rivets on the wall, and you got round portholes for windows. I guess that tells people I'm on a rocking ship, right? So, as the boogeyman comes in, this is going to get much more beautiful. Izabela says, I want to see how the 3D printer works. I have two of them. One's a really high-res one. It's an SLA machine. For those that don't know, I have a visual effects business and a model-making business, so in the other room back over there is my shop. I should give a complete tour of that, actually. I should do a video or live, maybe from the phone, and show people around, show them where we are and what we do. Hey, Richard McFarland, how you doing? The telescope is in the Arizona desert, and I am in Connecticut. So I set it up out there with the help of people in chat here, Marianne Robb, who's in the chat, and Tara Diulis, who's not here tonight, but she sometimes comes in. And so I think it's pretty cool that we can run this from all the way across the country. I spent the time to figure out the technology and get it to the point where we could just trust it to use it from all the way across the country. So we're looking good right now. Yeah. Let me read Izabela, what you say, what makes the move? Radiation? What are we talking about there? Did I miss something? How fast
clouds.
How fast the dark clouds. Well, you're right. It's the radiation and the radiation pressure, gravity of big stars. Because remember, these are particles. These are particles of silicates and carbon compounds. So these will be dragged around by gravity as well. So gravity can do that. And you can actually get the stellar winds to blow the gas around. The dust particles are more resistant to being moved. But don't forget, they're in a zero gravity environment, right? Other than the gravitational force felt by stars. Now, all the stars you see here, you tend to think that they're all like near the nebula. But they're not. This nebula is probably sitting all alone in space. And these stars are all probably several light years in the foreground or in the background. Some might be near the nebula. So they may not be, their radiation may not be doing anything to this dark cloud. And I mentioned it earlier tonight. This definitely looks like a candy cane. This dark cloud here, the densest part of this dark cloud are probably protected from the ultraviolet radiation that hot stars are producing. All right. And so that means that the life and planetary systems can form in the dark here. As I said before, and remember this, life began in the dark. And it's in those dark nebulae. That's my hot button. Dark nebulae are my hot button. I love dark nebulae because they lead to my next love, the primary love in astronomy, which is exoplanets. That's my specialty in astronomy, is exoplanets and trying to figure out details about exoplanets. But the thing that's interesting is that people look at these types of images, and because it's in two dimensions, they don't realize we're looking at three-dimensionality here. You know, this backside might be just as wide as this front side, but it's going away from us, so we don't see it. You put it like this, and maybe this is going to be the same size as down here. We don't know. We'd have to do a study. And usually, to figure that stuff out, they might do studies of neutral hydrogen in these regions and do radio studies of the neutral hydrogen because they emitted a certain frequency, and based on how much the spectral lines are shifted, we'll be able to tell details about the movement of the dark clouds. So it's really interesting how that works. So that's how we figure out galactic rotation. We do neutral hydrogen studies of the gas moving toward us, which is blue shifted, and the gas moving away from us, which is red shifted. So blue shifted gas coming toward us, by a certain amount we get a velocity, a speed. Going away from us, we get a velocity and a speed, obviously of rotation, and then we get the angle which is moving. So that tells us which direction the galaxy's rotating and how fast. And there's interesting relationships with the speed of rotation of a galaxy, which actually allows us to find out some fascinating details about the galaxy. You know, Mr. Django, how you doing? Nice to see you.
I was looking around online for information on 1622 here, and if you imagine the boogeyman is lying on his left side, sort of facing up, that would be his left hand extending down and then to the right. And there's that bright patch farther down, right there. That is amazing looking in some other images. If you have enough exposures, can you try to zoom in on that a little bit? I don't remember ever taking a close look at that before.
Yeah, this camera is better. We've actually got a smaller field of view, and we've nearly doubled the amount of pixels we have in that view. So the camera shows us a lot more detail. Actually, this particular camera is the ZWO 183 MC Pro. What does that mean? It means that it's a thermoelectrically cooled. If you notice the temperature is minus 20 Celsius on the sensor. What that means is we get less noise. And that's what the MC, the C means cooled. I'm sorry, no, the Pro means that it's a cooled, thermoelectrically cooled. And the C is color. It's a one-shot color. And this particular camera is really probably the most sensitive camera in the ZWO line. And the nice thing is this camera is literally tuned to our optical system, meaning that we get the best possible results with this particular camera combination with our telescope. You know, and by the way, Stefan Django, I want to send a shout out to you. You actually took a really, really beautiful photo of the sun the other day and posted it, and I want people to know where that is. Izabela, can you post a link for everybody, if you can? He took a photo of a sunspot group, and I thought it was really quite beautiful. And there we go. Thank you, Izabela. Yeah, that's just to give you an idea, because like I said, we want to do solar astronomy possibly on the East Coast and do all the other astronomy out west. And in time, we want to get a telescope in the southern hemisphere as well, so we can start exploring the Magellanic Clouds and a lot of the other locations down there that are just not available to us right now.
Oh, that's nice. The sunspot group.
Oh,
looks
yeah, isn't it pretty?
3576 has been prominent lately.
Yeah, Stefan did a beautiful job.
That's nice. Way to go, Django.
See, Stefan, it's not just us that want to give kudos. We want to let everybody else know if they've done some cool things. We're gonna let people know, man. And you did. That's a really, really beautiful shot. Yes, Richard. The camera is the 183 MC Pro. You know, the ZWO, ASI 183 MC Pro.
Izabela had a question.
Hey, Mike Townsend. Yeah. Oh, she was asking, I think, about... yeah, go ahead. I saw that she asked a question.
Let me find it. Are the different isotope ratios of elements always an indication that they're from another solar system?
My answer is that isotope ratios can tell us a lot about the interstellar space, not in our solar system. But you got to be really careful studying isotopes because we're not really sure yet in our vast knowledge of space, which is only 4% of the known universe. We're not sure yet how isotopes actually make their way to us from distant solar systems. But in general, there are isotopes that haven't been found here, literally. So they'll say, "Oh, they may have come from another solar system." Daryl, you can add what you want.
I wonder if she's not alluding to that thing by Abby Loeb she posted in our chat this morning.
The spherules that Avi found.
He was talking about isotopes and ratios and amounts of some certain elements, lanthanum and one was uranium, I forget the other one, that appear to be in ratios different than what we see here on Earth or in typical meteors or something.
Yeah, and what that says to me, and I know Avi,
she corrected me. Okay. No, Daryl, it was a general question, but thanks. All right, I'll shut up now.
No, that's fine, because he did mention isotopes. Now, like I said, I know him, and I trust his results. And if he says that an isotopic composition of a spheral is different from what we see, then he's certainly going to be correct about that. He wouldn't say things that aren't true. And he would also have done his due diligence, which he always does, to make sure that what he presents has been tested and peer-reviewed. And so there are other people, though, that don't believe anything he's saying about these things because, frankly, I think they don't. I don't think they believe that there's a possibility that there's extraterrestrial life out there, and that's a problem because we know it can be out there. We know that it's there, and it may very well have made it here. And we have, Brainius Balky. How you doing? Welcome. If you haven't subscribed to us, please subscribe. It's all free. You get pictures for free like we're taking here. And Brainius asked the question, do you think we're going to make it? I do. Actually, I think we're going to be fine. I do. As a species, I think we're going to make it. We don't have anything trying to kill us except the universe. So how bad could it be?
Famous last words.
Yeah. No, but I do think that our universe has been rather kind to us, at least modern humans. Keep in mind that we're here because the universe tried to kill us. 65 million years ago, the Yucatan Peninsula off the Yucatan, the impact over there, that particular impact caused a nuclear winter effectively, and the plant eaters died, the ocean plankton died off to some extent, and when the meat eaters couldn't find food, they died, and it was sort of a domino effect. And so that wasn't the first time. It was 252 million years ago when the Permian period was coming to an end, and this is what defined the end of the Permian period. There was a volcanic eruption in what's now Siberia, and this volcanic eruption spewed so much carbon dioxide into the air, gigatons, that's billions of tons of carbon dioxide. How much does an atom weigh, right? Imagine how many you have to make a pound of something, and then a ton of something. So you can see that we're talking billions of tons of carbon dioxide spewed into the air over the course of a few days to a few weeks. And what happened was that immediate impact was to raise the temperature on the Earth by 21 degrees Celsius. Okay? The greenhouse gas locked in the infrared, and it just was crazy. We didn't have the ability to bleed that extra off. We just didn't. So what ended up happening was the oceans warmed up, and oxygen in the oceans doesn't stay well in the solution if you have heat in the water. Hot water is less oxygenated than cooler water. So the plankton died, the oxygen levels dropped, and this is Permian period now. And thus the creatures in the ocean that couldn't handle it died. And so 96% of life died when that happened on this planet overall. That's a lot of creatures dying. However, what creatures love the heat? There are certain creatures that actually do very well in the heat, and they were relatively unaffected. In fact, they rose to prominence because all these empty niches from life that was previously filling them were now empty, and over time they evolved and moved into them. And those creatures were the animals that would become the dinosaurs. And thus, 252 million years ago, the age of the reptiles began. And it lasted until 65 million years ago. Talk about a successful set of species, huh? They were a very successful species on the planet. So, and 65 million years ago, waiting in the wings were the things that would become mammals. And back 252 million years ago, one of the things that happened was the creatures back then that were dominant were those that were tending toward mammalian life. So when the eruption wiped them out because they couldn't handle the cold, obviously that followed, and the heat that was the initial problematic impactor, they ended up basically dying out and kind of just sequestering themselves in these tiniest of little niches. And then when the Chicxulub impactor happened 65 million years ago, well, now they're waiting in the wings to come up, and now all these empty niches occurred. We no longer had dinosaurs. We no longer had these big reptiles. However, we had all these creatures that actually could now evolve and take advantage of the new environment, and the new pressures that were put on them were favorable to their further development. That's evolution followed by evolution, which is adaptation followed by mutation, or mutation followed by adaptation. So these creatures ended up flourishing and became mammals, which became us over time.
And
so
that's where I've talked about the Corral Bluffs before. It's a geologic area just immediately east of town here. It's one of the places where the KT boundary is exposed.
Yes.
And They have tracked development of mammals in this area after the
Yep.
Chicxulub impact,
Yep.
and
Yep.
little critters soon after the impact that were the size of, say, rats.
Voles. Like a
Within
vole.
a half,
Yeah.
within a 500,000 years, they had grown to the size of, evolved to the size of large hogs because they had a niche to grow into.
Yeah, and there was actually no environmental pressures that kept them down. In fact, all the environmental pressures favored their growth. You know, oxygen content in the atmosphere, temperature, water availability. It finally turned out that the Earth became a much more stabilized planet. You know, the early days on Earth were just tumultuous. I don't think that we didn't have life here for 2 billion years. And then around 2.5 billion years ago from today, we ended up with phytoplankton and blue-green algae, and those particular creatures ended up providing the oxygen atmosphere that we have. And that oxygen atmosphere that we have, it was building up in the atmosphere, and it's called a GOE, the Great Oxidation Event. It looks like it was fairly fast for some reason. Can't tell you why, but probably because there was a amazing jump in life, an explosion of life, so to speak. And when that happened, what happened at that point was, with the explosion of life and oxygen, now our atmosphere is building up an oxygen amount, a percentage. And that's visible to any creatures that are more advanced than us looking for planets like their own. If they're carbon-based life, they're going to look for a planet that has oxygen in the atmosphere, because that's what a carbon-based life form requires in order to make energy and to exist. Needs oxygen. So carbon-based life forms would find other planets that had oxygen in them. And our planet, contrary to Stephen Hawking saying we should keep down low and stay out of sight, our planet had other ideas. And about 2.5 billion years ago, when oxygen started building up, there was nothing that we could do about it. We weren't even a glint in a petri dish to anybody back then. But the fact is, that oxygen was seen potentially by other civilizations in the universe that had the capability to look for that. We're just getting that capability now. And we've only been around for about 4 million years if you go back to Lucy. Right? So, maybe it takes about
women.
Mars needs women, right? Maybe it takes about 4 million years or so for civilization to get advanced enough in order to start looking for planets like their own. But then it's going to take another, and now we're actually kind of on the downside, where we're going to be able to. It's going to be easier to make technology that allows us to get to the stars out there. One of the lectures I do around the country now has to do with interdimensional travel. It's not science fiction, actually. In fact, CERN built the Atlas accelerator over there, and the Atlas accelerator is being used in part to study these particular particles that show tremendous promise. And they're called Kaluza-Klein gravitons. And you heard me right, gravitons. It's rumored to exist, suspected they may exist, but they haven't been found yet. They're 10 to the 16th times more powerful than the gravitons holding you right now into your chair or on your couch or in your hands into the popcorn that you're eating while you're watching this on a big screen TV. I don't know. But those gravitons can be utilized to take us out of our 4 dimensions into a 5th dimension. And that 5th dimension is highly compressed. And within that 5th dimension, you could get a exit point and an entry point back into the 4-dimensional universe we live in. So you could travel without having to worry about the speed of light limit. That's something that's pretty cool. And that's neat. And that's one of the lectures I give now. I base it on a book by my friend Bob Schroeder called Solving the UFO Enigma, where he talks about string theory, and he goes into the hardcore physics of how it works, which no one can really understand. So I try to make it understandable, so that people can see what's really happening. Hey, Gavin Marshall, how are you? Says, this is so cool. Thank you. You don't get to see the interstellar weather very often. No, that's true. You don't. But now you can hear.
Can we zoom in on that white area?
I'm just about to, because I'm starting to see this beautiful feature that's made itself evident. Okay. This white area is a area where there is a dark nebula that has been illuminated by this star. And it'll pop in right there. There's this nice dark thing right here. I see some traveling lines here. This is called walking. It's a guiding artifact. So if I was to zoom out a little bit down the bottom, we're probably going to see a weird band. Let's find out. Or if it's not there. No, maybe not. But I mean, we're getting walking noise. But we can get rid of that. That's something we can get rid of. Right now out there, we're getting some wind. And you can see these red bars mean that the telescope is being subjected to some wind. And when that happens, this filter will not allow a photo to come in unless it falls into a certain level of circularity. And that's something that we want to avoid.
So it's 37 stacked, 30 ignored.
Yeah. So we're fighting wind, but that's okay. I'm gonna change this to the boogeyman, which is LDN 1622. And then we're going to save it like this. I mean, this is 37. This is more than enough. Although I have to say, I did stack 100 shots the other night when I was doing a private stream for myself, just doing stuff. It's pretty cool. Was Curtis Horn here?
He is now.
There he is. Hey, Curtis, how you doing? That's correct. Curtis Horn says you can increase the gain and lower exposure time when fighting the wind. Yeah, but look, I got this full width half maximum filter, Curtis. So I can just be patient and let my telescope and let the guiding system worry about it. But you're absolutely right. I could do that, but I don't want to raise the gain too much because I end up with a lot more noise. Right now, the optimal level of gain on this particular camera is about 100. I'm at 250, so I'm getting lots of noise in here that I don't really need. But I'm doing it so that the folks watching can see what we're looking at. Look at this beautiful, beautiful nebula.
Step out and see the whole thing now. The dark clouds moving to the upper left really pop out now.
Yeah, they're really pretty. Let me see if I go back here. See, we got a green one. We got a 38. Let's do a color correction, see if that changes anything. Oh, yeah. See, I did a color correction, and you see now the red is more appropriate. And look at this. This is so pretty. Let's see where it wants to process the main thing to. Yeah, a little bit lower, a little bit higher. So this dark patch here, see this? This guy up here is likely gravitationally bound, gravitationally contracting. We don't know if it's long like a cigar and into the page or, spherical. It could be spherical, Richard McFarland says, thank you for a great evening. I got to go find a pillow. Okay. Well, thank you for coming, Richard. Make sure you subscribe, by the way, and hang out with us. Again, it's all free. There's no charge for any of this. Unless you want to donate, you want to help us out, you can join our Patreon if you like. But great to see you, and please come again, Richard. Great to have you with us. Curtis Horn, you doing any talks lately? I was telling folks that I'll be doing a live studio audience with SkyTour Livestream out in Roswell, and then again at Contact in the Desert. So it's pretty cool. Curtis says, yes, I did one at APEC. APEC is like an astrophotography mini conference there. How many people were there, Curtis, at the conference? Yeah.
Mark, excuse me.
Thank you,
please.
Izabela. Sure. Okay, we got 38 shots. I think we're going to stop at that because we're not getting much further right now. Probably the wind. Probably the wind is what's causing it. So, but that's good because of the filter. We're not ruining our shots. We're only getting perfect images that are stacked. And I absolutely love that. So we're good. Okay. Now what we'll do is get back into our finder mode so we can actually go check out things here. Like that. And let's increase the size a little bit. All right. Let's go back now here to our Curtis, you put up his link. Excellent, thank you. I'm going to check that out later. After the stream, guys, check that out or make note of his address there, and you can go check out what he did. Okay. All right, so what we're going to do now is we're going to come down here. It's not that, I don't think. Yeah, first at 213. That's a cluster with nebulosity, and I looked for that last time. We looked at it last time. I think this is the guy we want. Yeah. We're going to go there. This is interesting. This is a fascinating location. We've talked about life beginning in the dark. We talked about areas in the sky where we actually see the potential for life beginning in the dark. And then there's regions like this one that we're going to close in on here shortly. And when we look at regions like this one, that's where you realize that the universe can be a pretty dangerous place. So for all the wonderful places we've seen, there are places in the universe that are very dangerous, and we want to be as far away from them as we can. This is one of those places. And I'm going to show it to you. We are far enough away from it. Excuse me. All right, this location is an object known as Thor's helmet. If you look where the telescope's pointing, it's just past the meridian, just past pointing south a little bit. And so we're getting this. This is about the best it's going to get for us right here. Okay. I think that's pretty good. We'll let that do the guiding. It's doing the guiding, and we'll do a 25-second shot. Let's first, you can see how the image bounces a little bit. Let's zoom in, make sure we're in focus. We may have to. Yeah, we're going to refocus. Have to refocus. So I'm going to make sure we take us fully out of focus and let the system put us back in focus.
I noticed when you did a focusing run earlier tonight, when you were defocused quite a bit, they made the stars made rings, and the bright spots of the stars were actually at the bottom of the rings. I was wondering if you didn't have a collimation problem, but those look pretty centered there.
Yeah. See?
Yeah.
Yeah.
I don't know what I was seeing earlier.
It's okay. I'm going to take us back down a little bit. All right, and go one more level, and then we'll start the process heading down into the negative, and this will start the process of focusing. Technically, before you do anything, photograph anything, you're supposed to refocus, guys, and I just choose not to. I like to. I mean, the telescope holds focus pretty well. Over here in this area, you can see there's a little temperature. It's 8.5 Celsius in the building right now. And whereas the temperature does drop a little bit, like I said, it's literally 8.5. So that's actually chilly. And down here, to hold the sensor at minus 20 Celsius within the camera, which is inside this opening here, inside this guy right there. You can see the tip of the camera right there. Camera's at the front of the telescope. It's not in the back. So to hold the temperature, we're only using 35% of the cooler processing power. In the summer, that could jump to 100%. Because it could very well be 115 degrees inside the building. When the building's closed, it could get up to 130, 135. Okay, so that's good. We know where we're going to go. Now we're going to do this. So we're going to center in our location where the best focus was found. There it is. So we get out of that. We take down this a little bit. The music is a little loud. Oh yeah, I forgot to mention, and thank you, Calabos. That's Michael. Thanks, Mike, for mentioning that. In order to be a winner in our equipment giveaway contest, you have to be a subscriber. Since it's free, it's not like you got to give away any money to be a winner. So I encourage you, if you haven't subscribed, please do, because then you can proceed to enter the contest online. They'll be done in the chat. I'll moderate it at the end of the night. I will tell you who wins, and if you can't stick around and you had entered a number for our contest, I will post it on the SkyTourLive.org website. and you'll see the previous winners, including your name if you win. Okay, let me do this. I'm going to drop down a little bit, and then we're going to go over just enough, like this, and going to head a little bit to the west. Okay. That looks good. Okay. 25,000 milliseconds. Here we are. And let's jump in and check it out. Oops. Didn't want to do that. I'll do this. Here's the boogeyman from last time. We're going to clear it. And there is the beginning of Thor's helmet. Look at that. Now, what is Thor's helmet? Thor's helmet is a feature in space that we see here, but what is it in fact? What is going on here is rather astonishing. This is an area in space where this star right here, okay, and as far as which star it is, I'll just make it very obvious. I'll just draw it over there. So this box is around the star. That's the source. And this star is known as a Wolf-Rayet star. That's wolf, like the animal, and Rayet, R-A-Y-E-T. And Wolf and Rayet were the astronomers that found this type of star. It's a star that is doing things unlike other stars we've seen. And what's happening there is the star is fusing like a normal star. However, for some reason, its outer envelope is energetically blasted off little by little, and it blows bubbles around itself, a cosmic bubble. And we're seeing that here, and this is the envelope around it, and you can see there's all this other stuff out here. Now you see the color green. From what we talked about before, you should know what that color means and why it's there. And it's there because it's ionized oxygen, as we talked about. But you'll notice there's some red areas too. These red areas are ionized hydrogen as well. So we're getting hydrogen and oxygen. Stands to reason that the envelope of the star is going to have oxygen and hydrogen in it, because hydrogen is the single most abundant element in the whole universe, and oxygen is the third most abundant element in the universe. By the way, carbon's number 4. So you can see why carbon-based life is probably a no-brainer for the universe. Okay. So let's see where this wants to go.
Isn't the Wolf-Rayet star on the order of hundreds of thousands to like a million times as bright as the sun?
Yeah, and I didn't mention the temperature either. The temperature of these stars is literally off the charts. I mean, I think you can have it up to 200,000 Kelvin if I don't miss my guess. But look that up if you could for me, Daryl, while you're doing that. Let's see. I want to make sure that I'm not just spouting nonsense here, because I recall that Wolf-Rayet stars can be exceedingly hot. I never did any research in astronomy when I was getting my degree on Wolf-Rayet stars, but I did pursue studying the elemental abundances in the interstellar medium created by them as well. Izabela, yes, oxygen. That's right, doubly ionized oxygen, which is O3 actually. not the O2. And the reason it's not a 2 is because the ground state of an atom is understood to be a Roman numeral 1. So oxygen with all of its electrons is O1. Singly ionized oxygen is O2. Doubly ionized is O3. See, we just love to confuse you. But that's how it is. So no one writes the 1 after a regular element because it's understood to be that.
If I caught your question correctly, Mark,
Yeah.
surface temperatures of Wolf-Rayet stars range from 20,000 K to around 210,000 K.
Okay, so yeah.
Hotter than almost all other kinds of stars. As far as brightness goes,
They're incredibly luminous.
I just saw that. Where was it? Hundreds of thousands for some Wolf-Rayet stars to over 1 million times the brightness of the sun for some others.
Yeah, I knew that you could have a 200,000 Kelvin temperature for a Wolf-Rayet star, but here's the thing about these Wolf-Rayet stars: they're short-lived, and when they start blowing bubbles like this, it's the beginning of the end, and they always end. They always end in a supernova. So we will see a supernova in this spot at some point in the future. And what's really interesting is we don't really know when. Won't that be cool if it happens like now?
One interesting thing about the Wolf-Rayet stars, they are extremely bright, but we don't see them as very bright because I guess their black body radiation, their peak radiation is far up in the ultraviolet.
Yeah.
So we don't see them as very bright.
Yeah, an ultraviolet study can certainly show them. O-type stars are among the hottest stars in the universe, and a lot of their radiation is given off in the blue end of the spectrum, and then farther past the blue end of the spectrum that we can see with our eyes, and that's in the ultraviolet range. So that's the reason why stars may not look that bright to us, but when you look at the total energy being given off by a star, it could be millions of times that of our sun, but you can still look at it and not say, oh, well, that's not so bright, because much of that energy is being given off in the ultraviolet range at that point. So that's interesting how how Wolf-Rayet stars operate. So they're going to go supernova. Go ahead.
Ultraviolet's what's making the gas fluoresce.
That's correct. Yeah, the ultraviolet energy causes the electrons to ionize. The electrons absorb this energy, and they wildly leap up in energy levels, energy states, until they actually can leave the atom. And of course, there's another oxygen atom that's going to be out there, and eventually it'll probably fall back into its own atom. But if it drifts around out there, it'll eventually find another oxygen atom. But when it does, the only time it gives off this green light is when it's falling back into the atom. So in areas that are really dense, you're going to get a pretty bright nebula because you're going to have lots of electrons falling back into their atoms and giving off light. When it's sparse, then you get a region like out here where it's not so bright, but you can actually see a subtle green glow here. So we're getting oxygen atoms having their electrons return and so forth. Now we've got 14 with 4 rejections. Let's find out where they are. Were they at the beginning? No, they're 2 at the beginning and 2 at the end. So that's good. We got a lot of good ones so far. But let's zoom in now so you can see the structure here. This is in a region where there's lots and lots of stars. Okay, so as you look at this, you can see all these tendrils. Now, you'll notice also, as I mentioned earlier, this red line right here. This is part of the original hydrogen envelope of the star that was ejected for some reason. There's more in here. There's more here. There's some out here that you can't really see. There's some right here that you can see. Okay, this hydrogen has been ejected, and the oxygen in the envelope of the star was also ejected. So this is a region in space where if you were close enough to actually sense the ultraviolet radiation pretty strongly, you would probably already be dead. It's a very, very, very dangerous region of space. If you're anywhere inside this bubble, everything in this bubble is absolutely sterilized. Yeah. And folks, please give us a thumbs up, will you? We do this for love. We don't do this to get any money out of it. We want to keep going. We want to keep presenting. We want to keep building telescope systems to take you on tours of the universe.
Aren't Wolf-Rayet stars pretty far off the main sequence?
They have their own category, I believe. The WR stars. I would look it up and find out where they fall on the main sequence. They're probably just like the sub-dwarfs have their own category. They're probably got their own category. I would expect that, yes. This is pretty. Very nice.
Of all the billions and billions of stars in the Milky Way, there are
not many Wolf-Rayets.
about 500, they say, in the Milky Way.
Yeah, that we found. We can't see on the other side. So
it says there's fewer than 1,000 Wolf-Rayet stars in all the rest of the local group galaxies. 166 known in the Magellanic Clouds, 206 in M33, and 154 in M31.
Well, they're rare. They're definitely rare stars. Izabela says, my PC is slow recently. I hope I didn't catch a bug or something. Well, Izabela, I would consider doing a little bit of maintenance on the computer in the following way. You can do a set of disk operations to basically defragment your hard drive. Because when you store files, they don't store it as one continuous piece. They'll put one here, they'll put a fragment way out here, a fragment down there. And so every time you access it, it takes longer to assemble all the fragments in order to actually run something or bring up a Word document or something. So I would recommend defragmenting your drive to begin with and doing a speed check at that point and seeing if it's any faster. It's going to be faster. So
I've noticed lately, too, that my system seems like ever since Microsoft tried that damn AI Copilot showed up on my computer, though I hope I got rid of it. It seems to be running quite a bit slower since then. They keep putting more and more bloat in the operating system.
Yeah, well, anytime Microsoft gets a hold of something, it just is destroyed. I can't say anything good about it, unfortunately. I wish I could, but I don't know.
I haven't used CC Cleaner in a long time. I should do that.
Yeah. Brainius talks about CC Cleaner, Izabela. That's another one to consider. Mike Townsend says, thinking about getting a Chromebook. Haven't you had a computer at home for a long time now? Huh. Interesting. Mr. Django says, use CC Cleaner before doing a defrag. Defrags are long. They take a long time. You can also get Glary utilities, Glary, Glary utilities. I have that as well. I mean, I'm storing so much data on these machines here, and I've got a whole suite of computers, ranging in size from micros this big to larger, big boxes with big brains like the one I'm running on now here in the control room. But they're actually, these little utilities are amazing. They do a great job. All right.
There should be an astronomical object called Thor's beer mug. Part of the mythology. I'd have to look it up.
Yeah.
He supposedly drank the ocean once. He had a beer stein or a beer mug that never went empty.
That's funny.
And they actually showed that in one of the Marvel movies where he's visiting Doctor Strange.
Yeah.
And he's in Doctor Strange's, library or whatever. And he's holding a glass of beer and it keeps filling up on it. So
that's funny. I like that.
Izabela says, Mark, give us an update on the all sky cam, please.
Oh yeah. I got it working really well, and I'm working with the author of it to do some fine tuning. Let's see, right now, I have it running now. It's outside running now here, testing. All Sky Camera is a ZWO 678 MC, and that's a one-shot color camera. And I tied it in with a Raspberry Pi and a publicly available free software called All Sky. And it makes, at the end of the night, it captures every single image that it takes, and you determine all that. And then it makes a time lapse every night. It makes a keyogram, which actually shows for each hour through the night. It shows you a slice of the sky to show you whether it was cloudy or clear. You just see a clear slice, or a cloudy slice, or something in between. And they give you the night at a glance and are great for studying trends. And then the last thing it does is star trails. The star trail image is really pretty. The only problem is I can't get it to do the star trails. I can do it manually. If I manually activate the programs that it does automatically, I get my star trails. When I don't, I just get a single frame. I don't get it. So Eric, one of the authors of the program, is working with me rather endlessly. Actually, very, very nice guy. Very, very helpful to get it to work. Brainius is asking a question. He says, what are we seeing there? Is it a light thing? If you're talking about what we're seeing here, you're seeing this star right here. And what's happening is it's actually creating this very high intensity radiation, which goes out from it in all directions. Okay. And as it goes out, what it does is it ionizes this gas that blew this bubble of gas from itself. And it ionizes the gas, driving the electrons off the atoms. And when they recombine with the atom, they give off light. In this case, the bulk of the gas here is oxygen, and the oxygen is doubly ionized here. And that means that when it rejoins, it makes this characteristic green light that we're seeing. There's also some red light here that you can see. There's just subtle red colors. This is hydrogen gas that's been ionized, right? And that hydrogen gas gives off a characteristic reddish light. Not a whole lot of it in here at the moment, so you can't see too much. But this area right here is very bright red when you process it. So there's a lot of hydrogen here. So this star is literally blowing cosmic bubbles. A lot of its atmosphere is being blown off with some radiative force because the stars are very hot. We talked about these Wolf-Rayet stars. They're a very special kind of star. They're very rare. They can be anywhere from 20,000 Kelvin at the surface to 210,000 Kelvin at the surface, as we talked about. And they generate a massive amount of radiative energy, and that radiation can tend to push away the very guts of the star itself, because only in the core of the star is fusion actually occurring. Only in the core. Outside, that's the stuff that's along for the ride. So in the core, if it gets really energetic, it can push those layers out, and that's what we're seeing here. It's pushed these layers out here of this star. You can literally see one of the cosmic bubbles here, and the previous bubbles that were blown off and scattered by radiation from other stars and radiation pressure from here, and ionized by this star here to look at the oxygen ionized so we can see the green. I hope that helps. Jessica S., how are you? Good to see you. You've been here a while. I didn't say hi. I'm sorry. So yes, it's a light thing. It's the way electrons, when they recombine, they give off light because they absorb energy to leave the atom, but then they give up energy when they go into the atom. And in space, when electrons rejoin an atom, in fact, in general, when electrons rejoin an atom, they give that energy back, and it's in the form of electromagnetic radiation, which is light. In this case, light we can see, which is green in this case. So again, this is Thor's helmet. We have 39. We're going to go for 40. And we got it. We got 40. So we're going to save it. Okay, and save it exactly as seen. All right. That's it. There we go. Thor's helmet. That came out nice. We got a good 40 images. Nice shaped stars. All good. Let's get back to our...
Do one more. I'm gonna have to split here, Director.
It's 1:30 in the morning here, so I have to get going too. But what one more would you like? Any requests?
First star to the left. Keep on straight till morning.
In other words, no.
That was a bad quote of James Kirk. From,
I remember
one of the movies.
Yeah.
Second star to the left. Keep on the morning. Well, golly. Yeah, I have a suggestion.
Want to do the beehive?
No.
Okay, what do you want to do?
Boday's Galaxy.
Oh, I think that's available.
It is. I was meaning to mention that earlier. That
Measure 81.
By this time of night, 81 and 82, the Big Dipper is actually very high up in the northeast now, and where M81 and M82 are now,
yep, we got them,
is almost overhead. That's in the head of the bear. It's farther up than...
Yeah, well, you look at the telescope. Telescope's heading up there. Yep, telescope's heading up there.
This sort of a presaging the galaxies of spring here.
Yeah. This will be the last object, assuming we can get there with no problem. Let's drop down. There's one. Let's drop down to auto mode here. Okay, there we go. That looks like M81 right there. And M82 will be just out of shot above. Well, not quite just out of shot because that's the old camera. With this camera, we got to go a little farther down. There it is. Okay. All right, Daryl, that's a good idea. So we'll do that. So what we'll do, let's head to the west a little. And I'll drop us down a little bit. Technically, taking pictures of M82 here, which is called a starburst galaxy, a spate of stellar production going on in there, and that's probably because of interactions with M81, which is this spiral galaxy. Now, you can't see the spiral arms yet, but we're going to take a picture of it so you can. And I'm going to focus on M81 tonight, okay? I'm going to bring that into view. I'm going to let M82 go out of view because I would like to focus on M81 and get a very nice shot of M81. And the next time we go, we can do M82. Beehive's not dull. It's really pretty. What are you talking about?
Yeah, it's all right.
Okay. So here we go. This is M81. This is a spiral galaxy in Ursa Major. And, okay, when we look at M81, and we talk about this galaxy, we're talking about a galaxy that is literally, oh gosh, it's 11, 12 million light years away, right?
Something like that, I think.
So, yeah, and M82 is relatively the same. So let's actually do a 25-second shot of this as well. This should guide okay if there's no wind, because it's actually so far north that the latitude and longitude lines are closer together, actually. So it doesn't have to go as far to make guiding corrections. So it might actually work to our advantage. Let's give it a try. Okay, underway. And this last image that will come up with the buffer showing you this is where Thor's helmet was, which is why it looks like that right now, because we got this going. I'm going to take down that value, go back to histogram value, and wait for M81 to come in. And make sure you guys, again, click the like, give us a thumbs up. Look at that. Now, where do you get this? This is live, man. This is the universe live in real time. You're seeing it live. You know? Just like that Spaceballs. Now, sir, you're seeing it now. Everything you see is happening now. What happened to then? We passed it. When? Just now.
Would this be the first you've done M81 with this camera?
Yes, it is.
Oh, I wondered, because it sure looks different than before.
Yeah, see, M81 with more pixels is beautiful, and we haven't... See, we got the camera at a time when M81 was not visible readily in the sky. And now it is. And this is another galaxy, by the way. This galaxy is interesting. And also near M81, there's another little dwarf galaxy that is here somewhere that we're gonna see it in a bit. Remember that dwarf galaxy?
Not offhand, no.
Well, it's right there. I think it's right there. Well, I'm gonna move in. Okay, and then we'll let this stabilize. Here we go. That's the dwarf galaxy right there, I believe.
Okay.
Now look at that beautiful dark lane. And we just see this was out of reach the last time we looked at it. We never saw any detail like this, guys, because the camera we used before, it was a 2-degree field, 2 degrees by 1.5 degrees in size, and fewer pixels to cover all that territory. Now we're 1.5 degrees by 1 degree with almost twice as many pixels or picture elements to capture detail. So now we're getting lots of detail. Look at that. Holy cow.
That's nice.
Yeah, I'm glad you thought of this. Thank you, Daryl.
Sure.
Daryl gets a gold star.
Oh, I was out 12:30 at night a couple of nights ago, and I saw, the location of M81 and the head of the Big Bear Ursa Major was pretty much due north of Polaris at its highest already. And
Yeah.
I said, damn, that'd be nice to look at. So I managed to remember it tonight.
Good for you. Thank you. And I see this is starting to show up again.
Yeah.
Yeah, it's a beautiful spiral. I'm going to try to pull in just a little more detail here. Okay, now that's going to pop in here in just a sec. Watch this. Bam. Look at that. Wow. Isn't that beautiful, guys? This galaxy, about 12 million light years away, Curtis made an observation. Curtis Horn made an observation about this. He said, there could be someone in that galaxy admiring our galaxy. That's true. Absolutely correct. Lubo in China. Hey, how you doing? Did you show Supernova in NGC 4416 already? No, I did not. Daryl, can you look up 4416 and find out if that's the same supernova you were talking about before?
Already on it.
All right. Michael Hendrick says, thank you for all. This is truly beautiful. Yeah, of course, man. This is beautiful. I love it.
No, it is a different one.
Okay.
This rings a bell. It's in Virgo.
Okay. Well, Virgo's coming up. Oh, by the way, on the all-sky camera, what I didn't mention is that when you go and look at it on the website, on the left side, there's icons that you can pick. You can pick the latest time-lapse, the latest Keogram, the latest star trails. And at the top is a little Cassiopeia shape. You click it, and the constellation overlay comes up, and it's beautiful. You can see where everything is, what's coming up. You can see the constellations. They're labeled. They're drawn out, and you can see what's coming up. It's really, really, really nice. And it shows you the latest image, so that's really cool. By the way, Mike Townsend, I forgot to say hi to you. I saw you out there. I'm sorry, man. But thank you for coming out. And again, to those that haven't subscribed, please look what you get for nothing, man. A galaxy, and you're going to be able to take this home because it's going to be on our server, and we're going to be actually, it'll be available to you to take and download exactly like you see it in the way we produce it here. Now, remember what I talked about with the longitude lines being closer together up north as we get closer to the pole? Requires less guiding. Look, we have 13 taken so far, 0 have been rejected. And that's because we don't have to worry about guiding so much. And now I can bring this way down. This will protect against any little wind burst that ruins a shot. 6.23 won't cause any, that right there, it's 6.23, won't cause any, problems. But look at that. Let's zoom in some more. What do you think?
Sure.
All right, now the galaxy's outside our view of top and bottom here. Okay, notice the blue and the spiral arms. The blue and the spiral arms, these are areas where young hot stars are forming because it's in those spiral arms where you're going to get the star formation occurring. And that's a whole class in itself which I teach, which talks about spiral arms and young stars evolution in these spiral arms. And I do talks all about those as well, about where the spiral arms come from, what we think, what are the different theories for how spiral arms form. If that stuff's interesting to you, on a cloudy night stream, what I may do is, instead of doing a stream where we're opening the observatory, if it's cloudy out there, I can actually do one of my talks for you if you like, or more than one talk. You let me know if you think that's interesting, and I'll take it to heart and do it if you want. Look at this galaxy right here. Is that a little elliptical or something right there? Looks it. Wow. This is really pretty. This is better than we've ever seen it. Of course, again, we're using it with a camera that literally is twice as good. You know? Well, Izabela, I don't know. Some people just want to see the pretty pictures. I get it. But thank you for that vote of confidence.
Galaxy seems more full than it has in the past.
Yeah, let's see where it wants to put these. It's gonna lighten it up a bit.
See some wispy structure in the spiral arms too.
Yeah, I see that. You're talking about down. What's that? Are you talking about up here? Or down here?
Down at about 6:30. Your pointer right there.
Right there, right?
And then there are other wisps up to the upper right at about 1 o'clock from the nucleus.
Like right here?
A lot of a little 1 o'clock.
Up here.
Higher
right,
up.
Right here.
Well, you can see it there too. But yeah, all through the spiral arms there. I mean, from about 3 o'clock up to 12 o'clock, directly above the nucleus, all the way out in the outskirts where the spiral arm is.
Okay, I dropped our mid-level setting down to reduce the intensity in here, and it shows more detail in here. Look at that! Wow!
Yeah.
Wow!
And then in the next arm out above that, where you were just pointing.
Up here, look at these knots of star formation, blue. This one splits off. Looks like it splits off and makes another one. Mm-hmm. Another spiral arm. Another wisp out here of a spiral arm. Now,
all the way over to about 3 o'clock.
You talking about here?
On the far right. 3 o'clock.
Right here?
Right there.
And now, because M81 and M82 are in the same relative physical location in space, it's very possible that M81 and M82 have been interacting with each other, yes, which could have caused star formation in this galaxy and the spate of star formation in M82 as well. So that's a really fascinating topic, is stellar formation in galaxies because of interactions. I'm going to drop this way down.
General idea.
Let's see what this shows us.
M82 is a starburst galaxy, I believe.
It is, yeah. We talked about that. All right, so now you can start to see the structure a lot more clearly. The nice thing about this is that we can go from literally blown out of the water, bright, okay, to taking it down to where we can barely see any details. And the reason is because of the fact that this camera allows us to have a lot of dynamic range. So we can go from blown out overexposed to minimal to show even more detail in the center. Now, if I bring this one up, this will actually show what's hiding in the background. Okay. And so that's what's there. Here, this galaxy shows up. It's really kind of a weird blue thing. And I'm not sure what that's all about. We got another galaxy here. Right? But this is only used for us when we're trying to see what's really going on there. Now, if I bring us back to a level of where we can see what's going on, do a quick color correction. Now, you might notice, as you said, the blue stars, but they also have these orangey yellow stars. These tend to be older stars. Now, that stands to reason because the galaxy's been around for a long time, but it's making new stars out in these spiral arms. The spiral arms are the turbulent areas in the galaxy. This is where pressure waves, I say pressure waves, shock waves from supernovae and so forth have pushed material and put it under compression against other material to start new star formation. So the very fact that the spiral arms exist shows that they actually are the regions where stars are being formed and thus delineating the spiral arms further. Wow, this is something.
Uh-huh. Is your full width half maximum holding up?
Yeah, we've got one rejected one, and let's find out. It's probably
okay.
close. Yeah,
Yeah,
look, 6.44.
I see that. That's really good.
Yeah, it is very good. So we're gonna have nice round stars, and I actually kept this at 6.23. So I didn't allow in even the 6.44, but now we're getting in the fives, so we're good. So we have 30 images here. I'm going to save it at this point and then save exactly as seen. That's beautiful. And so you can see what we're going to get. This is what we're going to get right there. This is the live image we just shot. This is what's getting shipped up. What you can't see is that galaxy right there. Okay. But it's actually in there as well. That's pretty cool. Let's see that galaxy. Look at that. And by studying noise here, you can see the noise is pretty regular. So that's actually very nice. Okay.
I can almost see a faint little...
Yeah, there's a thing in there, isn't there?
Little arm in that thing.
Yeah. Yeah, and that's way off to the side here. I don't think it's that faint. I mean, there is an arm in here. It looks like right there. We'd have to look and see. Look at this. This is beautiful. Well, guys, what do you think? We end the night with a beautiful galaxy. I think that is really a stunner. You can see these beautiful, young star formations here. Then the new stars that are formed out here. This is beautiful. Mm-hmm.
Nice ending.
Yeah. Okay, this is 34. We're going to go to 35, and then we're going to call it a night. I'm glad you guys enjoyed it. Thank you so much. On behalf of Daryl, I thank you for joining us tonight. I'm really having a good time tonight. As you can see, it's actually almost 2 a.m. I'm not even tired yet, but I know I have to go to bed. Yeah. I got a lot of work to do for History Channel, and they've got me... I'm working on 2 projects for them, and I've got another show that I've got to do all this analysis for. I've got to get that done. So I need to get my rest. But boy, oh boy. I'll leave you with this. When you look at this image, how many civilizations do you think might be looking at us from there? Kind of like what Curtis Horn was talking about before. But I often muse about, in a galaxy like this, it's a regular spiral. This is a spiral galaxy where it probably has not been put through too much of a tumultuous evolution. So it's had plenty of time, billions upon billions of years, to foster life. How many life forms are we looking 12 million light years away? How many are we looking at? Pretty cool. Wow. All right. I'll say one last time. And we'll say goodnight. Save exactly as seen. And good night to Measure 81. There we go. Fantastical.
Thanks for having me on, Mark.
Oh yeah, it's been great. I know you're tired and you got to run. So what I'll do is say good night to everybody, and I hope you guys are gonna have a good night. All right. We'll talk to you again. And again, subscribe if you haven't already. Consider joining our Patreon. We'd love to have you. So you guys have a good night, and we'll see you on the very next stream. So long, everybody.
Good night, everybody.